A tooth lies half exposed in a band of gray stone, not clean and white like the teeth in a museum drawer, but dark, weathered, and broken at the root. It has come loose from a cliff after rain. Mud has slumped down the slope around it. Grass roots hold the upper bank together, and below them, in a layer that once belonged to a river, the tooth has waited for more than 66 million years. Its edge is still serrated. Each tiny notch is a cutting surface, made for flesh, made for a living mouth, made for an animal that walked through the last forests of the dinosaur age in North America. If you kneel beside that tooth, the modern landscape does not disappear all at once. There is still wind. There is still dust. There are still insects moving through the weeds above the outcrop. But the stone has its own geography. It remembers a coastal plain, a river channel, a stand of cypress-like trees, a carcass dragged into shallow water, a predator leaning down with the weight of its skull balanced over the mud. The tooth is small enough to hold in a hand, but it belongs to a world that was continent-sized. This world was not the America on your map. No highways crossed it. No cities stood on it. Its eastern and western halves were divided for long stretches by an inland sea that reached from the Arctic to the Gulf of Mexico. Its shorelines shifted as water advanced and retreated. Its mountains were younger. Its forests were warmer. Its animals moved through coastal swamps, upland floodplains, volcanic ash fields, polar woodlands, and river deltas where the banks were soft enough to take a footprint and firm enough, sometimes, to preserve it. The Cretaceous period began about 145 million years ago and ended 66 million years ago. It was the final period of the Mesozoic era, and it lasted nearly 80 million years, longer than the entire time that has passed since the non-avian dinosaurs disappeared. To say Cretaceous America is to talk about a changing continent across an immense span of time. It includes the earliest flowering plants spreading into old conifer forests, the rise of duck-billed dinosaurs and horned dinosaurs, the last great tyrannosaurs, and the final ecosystems that existed before the asteroid struck. If this kind of journey into deep time is what brings you back to Jurassical, subscribing simply keeps the next one close. The title sounds like a kingdom, but it was not one kingdom in the human sense. It had no borders, no ruler, no throne. It was a kingdom made of habitats. It was built from rivers, seaways, floodplains, coastlines, plant communities, migration routes, nesting grounds, and the long pressure of evolution. Its rulers were not crowned. They were hatched, raised, scarred, replaced, and buried. Some left skulls and teeth. Some left eggshell. Some left tracks in mud. Some left nothing at all except the lineages that came after them. The last dinosaur kingdom in America did not appear suddenly at the end. It was assembled over tens of millions of years. The creatures of the final million years, Tyrannosaurus, Triceratops, Edmontosaurus, Ankylosaurus, Pachycephalosaurus, and their neighbors, were the final shape of a much longer story. Behind them stood earlier worlds of sail-backed predators, long-necked giants, armored herbivores, coastal crocodilians, flying reptiles, marine lizards, and small feathered hunters moving through brush at the edge of sight. To understand the end, you have to follow the continent as it changes. You have to watch the sea enter the middle of North America and divide the land into Western Laramidia and Eastern Appalachia. You have to watch the Rocky Mountains begin to rise. You have to watch the inland sea retreat and leave behind plains thick with rivers. You have to watch flowering plants become common and new herbivores learn to process them. You have to watch tyrannosaurs grow from smaller predators into animals whose skulls became the main weapons of their bodies. The evidence for all of this is not complete. It never is. Fossil records are uneven by nature. A river preserves one animal and destroys another. A hill exposes one bone and hides 1,000 more. Much of eastern North America was eroded, drowned, forested over, or never preserved in the right way. Even in the West, where the record is richer, the past comes to us in fragments. A jaw, a toe bone, a claw, a patch of skin impression, a bed of eggshell crushed into sediment. The kingdom is known through broken things. Still, the pieces are enough to build a world. A hadrosaur jaw with hundreds of teeth tells us about chewing. A ceratopsian frill tells us about display, growth, injury, and species recognition. A tyrannosaur tooth tells us about bite force and feeding. A layer of volcanic ash helps date the animals around it. A coal seam tells us that plants grew in wet lowlands for long enough to accumulate and be buried. A shoreline deposit tells us where the sea once pressed into the continent. The Cretaceous was not a single scene. It was a film longer than imagination wants to hold. At its beginning, North America still carried many Jurassic inheritances. At its end, the continent held some of the most familiar dinosaurs that have ever lived. Between those points, entire ecosystems appeared, shifted, and vanished. An animal alive in the early Cretaceous would have been separated from Tyrannosaurus by more time than Tyrannosaurus is separated from us. In the earliest Cretaceous, the continent was still recovering from the changes that closed the Jurassic. The great sauropod dominated systems of the Morrison Formation had faded from much of the northern interior. The familiar late Jurassic communities of Stegosaurus, Allosaurus, Apatosaurus, Diplodocus, and their neighbors no longer held the same world together. New plant communities were taking shape. New river systems cut across the land. New predators and herbivores moved into ecological space that had opened as older faunas disappeared. In western North America, early Cretaceous rocks such as the Cedar Mountain Formation and Cloverleaf Formation preserve part of this transition. They do not show the final dinosaur kingdom yet. They show its foundations. There are iguanodontian herbivores, early relatives of the duck-billed dinosaurs. There are armored dinosaurs, some with heavy plates embedded in the skin. There are long-necked sauropods still present in places, including animals that could reach enormous size. There are predators whose bodies still belong to a world before tyrannosaurs became dominant. One of the most striking predators of early Cretaceous North America was Acrocanthosaurus, a large theropod from the southern part of the continent. Its name refers to the high spines along its back, raised ridges of bone that supported a ridge of muscle or tissue running over the shoulders and hips. It lived long before Tyrannosaurus, but it occupied a similar top predator position in its own ecosystems. Its skull was long, its teeth were sharp, and its body suggests an animal capable of taking on large prey in open woodland and floodplain environments. Imagine a river flat in what is now Texas or Oklahoma, not as desert or prairie, but as a warm Cretaceous landscape, with channels cutting through sediment and stands of conifers, cycads, ferns, and early flowering plants. A heavy herbivore moves ahead of the waterline. It lowers its head to feed. The predator does not need to become a monster in the telling. It only needs to be an animal doing what large predators do. It closes distance when the chance is there, and the bones left behind will never record the full movement of the hunt. Acrocanthosaurus is part of a larger truth about Cretaceous America. The tyrannosaurs did not always rule it. For much of the early and middle Cretaceous, other large theropods held the role of apex predator in North America. Carcharodontosaur-like forms and related lineages were important in some regions. Later, as the Cretaceous moved on, these older predator groups declined in North America, and tyrannosaurs rose into their place. The final kingdom was built on a turnover of predators as much as herbivores. The timing of that turnover is not always clean. Fossils are rare in some intervals, and entire chapters are represented by scattered bones. Paleontologists work with what has been preserved, not with a perfect census. A missing animal in the rock does not always mean it was missing from the living world. It may mean the rocks are not there, or the environment did not preserve bones, or the bones have not yet been found. In Cretaceous America, uncertainty is part of the map. Small predators also mattered. Deinonychus, from the early Cretaceous, was not the largest hunter in its world, but it changed the way many people thought about dinosaurs. Its sickle-shaped second toe claw, long arms, grasping hands, and lightly built body suggested an active, agile animal. Its fossils, found in association with the herbivore Tyrannosaurus in some deposits, helped inspire the modern view of dinosaurs as dynamic animals, not slow reptiles dragging themselves through swamps. Picture Deinonychus at the edge of low vegetation, head moving, eyes fixed on a sound under the leaves. Feathers or feather-like covering likely softened the outline of its body, especially if relatives are any guide, though exact covering is not preserved for every species. It would not have looked like a scaled lizard with oversized claws. It was a theropod close to the line that would eventually include birds, a predator whose body carried hints of speed, balance, insulation, and display. Tyrannosaurus, often imagined only as prey, deserves its own attention. It was a large herbivore, not enormous by dinosaur standards, but substantial, with a long tail and a body adapted for browsing. Its jaws and teeth-processed plant matter in ways that point toward the later success of more advanced ornithopods and hadrosaurs. Animals like Tyrannosaurus show that the herbivore side of the Cretaceous story was changing steadily. Chewing, gut capacity, posture, and social behavior all mattered in landscapes where plants themselves were evolving. Flowering plants were one of the great changes of the Cretaceous. They did not take over the world overnight. Early in the period, conifers, cycads, ginkgos, ferns, and horsetails were still major parts of many environments. But angiosperms spread and diversified through the Cretaceous, changing forests, riverbanks, insect communities, and the diets available to herbivores. By the end of the period, flowering plants had become far more prominent, though the world still retained many older Mesozoic plant groups. The arrival of flowering plants did not make the Cretaceous suddenly modern. There was still no grassland in the way we know it today across most dinosaur habitats. Broad, open prairies would belong mostly to later ages, but the presence of flowering shrubs, small trees, and eventually more diverse plant communities changed the texture of the land. Leaves, seeds, fruits, flowers, and new insect relationships altered the lower layers of forests and the edges of waterways where smaller dinosaurs fed. A fossil leaf can seem less dramatic than a skull, but it is one of the quietest ways the world speaks. The veins in a leaf tell you something about growth and water. Its shape hints at climate. Its abundance in a bed of shale can tell you that plants were shedding into still water, perhaps an oxbow lake or floodplain pond. Beside those leaves, a small tooth may appear, then a turtle shell, then the bone of a fish. The ecosystem returns not as a panorama, but as a drawer full of pieces. During the early Cretaceous, Western North America was already being shaped by tectonic forces along its margin. Oceanic plates were descending beneath the continent, deforming the crust, raising highlands, and helping create the basin that would later receive the Western Interior Seaway. Volcanism to the west sent ash into the air. Some of that ash settled over floodplains and lakes, later becoming bentonite layers. Those layers can be dated, matched across distances, and used as time markers within the rocks. The Western Interior Seaway became one of the defining features of Cretaceous North America. It did not appear in one simple flood and remain unchanged. It advanced and retreated in pulses as sea level, tectonics, sediment supply, and climate shifted. At times, it connected the Arctic Ocean with the Gulf of Mexico, turning the middle of the continent into a long, shallow marine corridor. The land to the west is called Laramidia. The land to the east is called Appalachia. That division matters because it shaped dinosaur evolution. Populations on one side of the sea were separated from populations on the other side. Western dinosaurs are much better known because the rocks of Laramidia are more exposed and fossil-rich in many places. Eastern dinosaurs are harder to recover, and their record is more fragmentary. But they existed. The continent was not empty east of the sea. It was simply less generous to paleontology. At its greatest extent, the Seaway made North America feel less like a continent and more like two long, shifting islands. Laramidia stretched along the western margin, narrow in places, bordered by water on one side and rising mountains on the other. Appalachia lay to the east, lower and more humid in many reconstructions, with rivers draining toward the Atlantic and the inland sea. Dinosaurs lived on both lands, but the rock record gives one side a louder voice. The Seaway also created its own world, one that belonged to marine reptiles, fish, ammonites, sharks, turtles, pterosaurs, and diving birds. In the chalks and shales of Kansas and surrounding states, bones of mosasaurs, plesiosaurs, fish, and pterosaurs record a marine ecosystem that was not secondary to the dinosaurs on land. For millions of years, the heart of America was ocean water. Where wheat fields and roads exist now, fish scattered under the shadow of great swimming reptiles. The Niobrara chalk preserves part of that sea in pale stone. It formed from the accumulated microscopic skeletons of plankton, settling over long spans of time onto the seafloor. In that soft white record lie the bones of Siphac, a large predatory fish, the long-necked plesiosaur Elasmosaurus, and mosasaurs that became some of the dominant marine predators of the late Cretaceous. Above them flew pterosaurs. Below them, carcasses settled into low-oxygen mud where decay slowed and preservation became possible. This marine world helps explain the terrestrial one. The Seaway was a barrier, a climate influence, a corridor, and a source of sediment. Its shoreline environments were rich places where rivers met saltwater, where deltas spread, where plants grew in wet coastal plains, and where dinosaur bones could be buried quickly. Some of the best fossil records on land formed near the shifting margins of this inland sea, where water and sediment were always moving. The word America can mislead here. We are speaking mostly of North America, and within that, often of Western North America, because that is where the fossil record is strongest. Modern political boundaries do not apply. A dinosaur did not know Montana from Alberta, Utah from New Mexico, Texas from Coahuila. It knew river corridors, plant cover, nesting sites, dry seasons, predators, and the shape of the land as experienced through movement and survival. Laramidia, the western landmass, became one of the richest dinosaur landscapes ever recorded. But it was not the same from north to south. During parts of the late Cretaceous, paleontologists have debated whether distinct northern and southern dinosaur communities existed, especially among horned dinosaurs and duck-billed dinosaurs. Some evidence suggests regional endemism, with related animals differing along the length of the landmass. Other studies warn that sampling and preservation can create patterns that look stronger than they were in life. This is one of the reasons the Cretaceous record remains alive scientifically. New fossils do not just add names, they test old maps. They change the apparent ranges of animals. They reveal whether a dinosaur was local, widespread, short-lived, or part of a lineage moving through time. A single skull from the right layer can redraw the relationships between regions. A single ash bed can change the age of a fauna. A single tooth can show that a predator lived farther south or later in time than anyone had known. In southern Laramidia, formations such as the Kaiparovitz Formation of Utah preserve a warm, wet, late Cretaceous world. The sediments speak of rivers, floodplains, ponds, and coastal lowlands near the western edge of the inland sea. This was not an open desert. It was a place of thick vegetation and high productivity, able to support large herbivores and the predators that followed them. The animals here were not just smaller versions of northern species. Some were distinctive. A horned dinosaur skull from southern Utah does not simply show an animal with horns. It shows a local variation in a continent-wide experiment. Ceratopsians evolved frills, brow horns, nose horns, spikes, bosses, and elaborate skull shapes that likely combined display, species recognition, combat, and social signaling. In the Kaiparovitz rocks, animals such as Cosmoceratops and Edmontosaurus show how far that experimentation could go. Their faces were not decorative in the human sense. They were biological signals made of bone. Cosmoceratops had one of the most ornamented skulls known among horned dinosaurs, with a frill and horn arrangement that seems almost excessive until you remember that evolution often builds structures through social pressure as much as survival pressure. Horns can deter predators, but they can also identify species, attract mates, intimidate rivals, and communicate maturity. The skull becomes a billboard, weapon, and passport all at once. In a land where several large herbivores shared space, being recognizable mattered. Predators moved through these same southern habitats. Tyrannosaur relatives such as Triceratops belonged to a phase before Tyrannosaurus itself, showing that tyrannosaurids were diversifying across Laramidia well before the final Maastrichtian. Their skulls were deepening, their bodies growing more powerful, their teeth and jaw mechanics moving toward the heavy-headed predatory style that would culminate near the end of the period. The final tyrant did not appear from nowhere. It had ancestors, cousins, and earlier experiments. Hadrosaurs also thrived in these southern landscapes. Duck-billed dinosaurs were among the great success stories of the late Cretaceous, with dental batteries made of many tightly packed teeth that could grind plant material more effectively than the simpler teeth of earlier herbivores. They were not ducks in any meaningful way beyond the shape of parts of the snout. They were large, complex herbivores, many of them capable of moving on 2 legs or 4, feeding through a combination of strong jaws and sophisticated tooth replacement. A hadrosaur mouth was a processing machine. New teeth formed as old teeth wore away. The chewing surfaces were not made from a few permanent teeth, but from stacks of teeth working together. This allowed hadrosaurs to exploit plant resources efficiently, including tougher vegetation that would have challenged many earlier dinosaurs. In ecosystems with flowering plants, conifers, ferns, and other growth along floodplains, this mattered. Chewing was part of their success. The North had its own richness. Dinosaur Provincial Park in Alberta preserves one of the great late Cretaceous dinosaur assemblages in the world. Its rocks belong largely to the Campanian stage, older than the final Hell Creek ecosystems, but already filled with highly specialized dinosaurs. Bone beds, articulated skeletons, isolated teeth, turtle shells, crocodilian remains, fish, plants, and invertebrates all contribute to a picture of coastal plain life near the inland sea. In that northern world, herds of hadrosaurs moved through lowlands where rivers shifted and left oxbow lakes behind. Ceratopsians fed among vegetation and carried skulls that changed through growth. Ankylosaurs, plated and low to the ground, moved like living fortresses through the same habitats. Above the smaller channels, pterosaurs may have passed, and in the water, turtles and crocodilians waded in the slow places. The landscape was full, layered, and alive in ways a single mounted skeleton can never show. Corythosaurus, Lambeosaurus, Parasaurolophus, Centrosaurus, Styracosaurus, Chasmosaurus, and others belong to the broader late Cretaceous richness of Western Canada and nearby regions, though not all lived in the same exact place or moment. Their names often appear together in books, but the rocks keep better order than imagination does. Each species belongs to a particular interval, a particular formation, a particular set of environmental conditions. Time separates neighbors that museum halls often place side by side. That is one of the quiet corrections paleontology makes. It teaches that the dinosaur age was not a crowded room where every famous animal stood together. It was a sequence of communities. The world of Dinosaur Park was not the world of Hell Creek. The world of Kaiparowitz was not the world of the Cloverleaf. The animals that seem close to us because they are all extinct may have been separated from each other by millions of years, longer than many mammal groups have existed in recognizable form. Tyrannosaurs in the Campanian North included animals such as Gorgosaurus and Daspletosaurus. They were large predators, but they were not Tyrannosaurus rex. Their bodies and skulls show stages in tyrannosaur evolution, with powerful heads, reduced forelimbs, and increasingly specialized feeding anatomy. They lived alongside abundant horned dinosaurs and hadrosaurs. And their bones sometimes carry injuries, pathologies, and tooth marks that show lives full of conflict, feeding, healing, and risk. A Tyrannosaur skull is not just a symbol of violence, it is a record of force distribution. The thick bones of the snout, the arrangement of teeth, the jaw muscles, and the reinforced palate all point to an animal whose head carried much of its killing equipment. As tyrannosaurs evolved, the arms became smaller relative to the body, but the skull became larger and stronger. The animal did not need long, grasping forelimbs in the same way an allosaur might have. Its face had become the main instrument. Ceratopsians answered predator pressure with their own forms of strength. The frill, horns, beak, and heavy neck musculature of a large horned dinosaur created a front end that was difficult to ignore. It is too simple to say every horn evolved only to fight predators. Many likely functioned in display and social contests, but a large ceratopsian facing a predator would not have been helpless. The head could swing, the horns could wound, the body behind them could weigh several tons. Predator and prey were not locked in constant battle. Most days were not dramatic. Most animals spent more time feeding, walking, resting, growing, avoiding heat, seeking water, and interacting with their own species than fighting for their lives. The fossil record tends to preserve extremes because bite marks and broken bones draw our attention. But the normal life of Cretaceous America was built from ordinary repetition. A herd moving toward a river, a juvenile staying close to adults, a predator choosing not to attack because the risk was too high. The Two Medicine Formation of Montana offers another kind of evidence: nesting grounds. Maiasaura, a hadrosaur whose name means good mother lizard, became famous because of nests, eggs, juveniles, and growth series that suggested complex reproductive behavior. The details of dinosaur parenting varied by species, and caution is necessary. But the site helped show that at least some dinosaurs nested in colonies, and that young animals could remain associated with nest areas after hatching. Eggshell is fragile, but in the right sediment it can outlast mountains. Broken fragments in a nesting horizon can tell us where animals return to lay eggs. The arrangement of nests can suggest spacing. The bones of hatchlings and juveniles can hint at growth. A nest does not preserve a voice, a body warming eggs, or the movement of adults between clutches, but it brings the story closer to behavior than a single isolated limb bone ever could. Maiasaura also reminds us that dinosaur lives were not only about adult size. The Cretaceous was full of babies. Nests held embryos. Hatchlings left the egg with proportions different from their parents. Juveniles occupied ecological spaces adults did not. A young hadrosaur was not simply a smaller adult in practical terms. It faced different predators, ate different amounts, moved differently, and lived under different risks. Many dinosaurs never reached adulthood, and the success of a species depended on producing enough young that some survived. Growth studies from dinosaur bones often use lines of arrested growth, vascular patterns, and bone microstructure to estimate how quickly animals grew. Some dinosaurs grew fast, especially large theropods and hadrosaurs during parts of development. Growth was not uniform forever. It slowed as animals reached maturity. A bone slice under a microscope can show the pace of a life in a way the outside of the fossil cannot. The animal becomes not just a skeleton, but a biography written in tissue. The Cretaceous atmosphere and climate also shaped these lives. Overall, the period was warmer than today, with high sea levels and no large permanent ice sheets through much of its duration. But that does not mean every place was tropical or every year was stable. There were seasonal changes, regional climate gradients, droughts, floods, storms, and long-term shifts. A dinosaur on a coastal plain experienced weather, not an average. Floods were especially important to fossil preservation. A river overtopping its banks could kill small animals, scatter bones, bury a carcass, or lay down sediment over tracks. A channel cutting through older deposits could exhume bones and redeposit them downstream. Many dinosaur fossils are preserved because water moved sediment quickly enough to cover remains before scavengers, weather, and decay destroyed them. The same river that fed the ecosystem could become the reason we know it existed. Volcanic ash layers added another kind of clock. In western North America, ash from eruptions to the west could settle across floodplains, lakes, and coastal environments. Over time, ash altered into clay-rich bentonite. Because volcanic minerals can sometimes be dated radiometrically, these layers help tie fossil communities to numerical ages. Without them, many formations would be harder to arrange in time. The ash is a reminder that the dinosaur kingdom was also a geological system in motion. Mountain building along the western margin of North America changed drainage patterns and sediment supply. As uplands rose, rivers carried eroded material eastward into basins near the seaway. Those sediments built floodplains and deltas, burying plants and animals. The same tectonic forces that lifted landscapes also helped create the environments that preserved dinosaurs. The final kingdom was not only biological. It was constructed by crust, water, sediment, and time. Appalachia, the eastern landmass, is harder to see. Its fossils are rarer, often more fragmentary, and frequently come from marine or coastal deposits where bones washed in from land. Yet it was a real dinosaur world. Hadrosauroids, nodosaurs, tyrannosauroids, ornithomimosaurs, and other dinosaurs lived there during parts of the Cretaceous. Their record is incomplete, but incomplete is not empty. The eastern forests had their own histories, most of which remain less visible. Dryptosaurus is one of the better-known predators from the eastern side near the end of the Cretaceous. It was a tyrannosauroid, but not Tyrannosaurus. Its remains suggest a large theropod with powerful arms compared with the tiny forelimbs of the later giant tyrant. Its original discovery in New Jersey in the 19th century helped shape early American paleontology, long before the Western bone rush made the public imagine dinosaurs mainly through the Rockies and plains. Dryptosaurus reminds us that the eastern record has its own importance. A partial skeleton from a greensand or coastal deposit may not give the same completeness as a Montana quarry, but it shows that isolated lineages were evolving away from the better-known western faunas. Appalachia may have held animals that looked unusual compared with Laramidian relatives, simply because they had been separated by the seaway for so long. Isolation is one of evolution's oldest tools. Along the Atlantic and Gulf coastal plains, the dinosaur world touched beaches, estuaries, lagoons, and swampy lowlands. Bones could wash from rivers into nearshore marine settings, mixing land animals with shells, shark teeth, and marine sediments. A hadrosaur bone in such a deposit is not only the record of an animal, it is also the record of transport, decay, and burial. It may have traveled after death, moved by water from forest to coast. Hadrosaurus, from New Jersey, holds a special place in the history of dinosaur science. Its discovery in the 19th century helped show that some dinosaurs were upright, active animals rather than sprawling reptiles. The mounted reconstruction became one of the earliest public dinosaur skeleton displays. The animal itself lived far earlier than the final Hell Creek fauna, but its scientific afterlife helped build the idea of American dinosaurs in the public imagination. Eastern North America has also produced evidence of armored dinosaurs, including nodosaurs. Unlike the club-tailed ankylosaurids famous from western deposits, nodosaurs generally lacked a large tail club but carried heavy body armor. In an eastern ecosystem with different predators and plant communities, that armor still mattered. A low body, a broad back, and bony plates embedded in the skin provided a defense strategy that did not depend on speed. The sparse Appalachian record creates a different kind of evidence. In the West, we can often speak in communities. In the East, we often speak in glimpses: a jaw fragment, a limb bone, a tooth, a track, a name attached to partial evidence. That can be frustrating, but it is also honest. The past is not obligated to preserve itself evenly. Some worlds come to us as crowded fossil beds. Others come as a handful of bones dredged from greensand or found in a stream bank. There is loss even before extinction. Not the loss of the animals themselves, but the loss of information. Entire landscapes of Appalachia may have held dinosaurs as strange and varied as those in the West, and most of that record may be gone or buried beyond reach. Paleontology is not only discovery, it is also the study of absence, of why some places speak clearly and others barely speak at all. Far to the north, another part of Cretaceous America complicates any simple picture. Alaska was not locked in ice the way modern imagination might expect. During the late Cretaceous, high-latitude ecosystems supported dinosaurs through seasonal extremes of light and darkness. The Prince Creek Formation has produced evidence of hadrosaurs, ceratopsians, tyrannosaurs, small theropods, and other animals living in polar environments. These dinosaurs were not tourists passing through a warm vacation coast. Many appear to have been residents. A polar dinosaur forest is one of the most remarkable images in the Cretaceous. For part of the year, the sun would stay low or vanish for long stretches. Plants would endure months of limited light. Temperatures were warmer than modern Arctic conditions, but seasons still mattered. Snow may have fallen. Rivers may have frozen at times. Animals had to cope with darkness, cold snaps, and food changes. The dinosaur age was not only heat and swamp. Dinosaurus, a smaller tyrannosaur from northern Alaska, suggests that top predators also adapted to these high-latitude systems. Its remains are limited, and reconstructions should be cautious, but the idea of a tyrannosaur living under polar light changes the emotional shape of the group. Tyrannosaurs were not just animals of southern floodplains. They belonged to a wide range of environments. Their lineage had become flexible enough to occupy forests near the top of the continent. Hadrosaurs seem to have been especially successful in some polar settings. Their dental batteries, large bodies, and possible social behavior may have helped them exploit seasonal vegetation. Herds moving through high-latitude floodplains would have faced pressures different from their relatives farther south. Predation, winter scarcity, nesting timing, juvenile survival, and migration all remain areas of study and debate. The fossils do not show a complete calendar, but they show that dinosaurs were living where the calendar mattered. The image of a juvenile hadrosaur bone from Alaska carries a particular weight. It means reproduction was happening near high latitudes, or at least that young animals were present there. Small bones are easily destroyed, yet some survived. In the dim season, young dinosaurs would have moved beneath conifers and deciduous plants adapted to darkness, surrounded by insects, small mammals, turtles or amphibians in warmer months, and predators that knew the same routes through the trees. Cretaceous America was not a single climate, a single fauna, or a single mood. It ranged from warm coastal lowlands to inland floodplains, from southern river systems to northern forests with long winter nights. The final kingdom was powerful because it was varied. Dinosaurs were not confined to one narrow way of life. By the late Cretaceous, they had occupied nearly every large-bodied terrestrial role available on the continent. By the Maastrichtian, the final stage of the Cretaceous, the Western Interior Seaway was retreating. The long marine barrier that had divided the continent was shrinking and breaking apart. Coastal plains expanded in some regions. River systems reorganized. Habitats that had once been near shore became farther inland, while other areas still felt marine influence. The familiar final dinosaur communities of Western North America developed in this changing geography, not in a static world waiting for an asteroid. The Hell Creek Formation, along with roughly equivalent formations such as the Lance, Frenchman, Scholard, and others, preserves part of the last few million years before the end Cretaceous extinction in Western North America. These rocks were deposited in river channels, floodplains, ponds, swamps, and coastal plain settings. They contain dinosaurs, turtles, crocodilians, fish, mammals, plants, invertebrates, and the sediments that held them. They are not just dinosaur layers, they are ecosystem records. A Hell Creek outcrop can look ordinary from a distance, Slopes of gray, brown, and tan sediment erode under open sky. Grass covers the higher ground. A person walking the surface scans for shapes that do not belong to the weathered mudstone around them. A bit of enamel catches light. A piece of turtle shell shows its texture. A rounded bone surface emerges from the slope. The last dinosaur kingdom often begins as something small underfoot. The famous animals of Hell Creek did not know they were famous. Tyrannosaurus did not know it would become the symbol of extinction and power. Triceratops did not know its skull would hang in museums as the face of resistance. Edmontosaurus did not know its bones would help reconstruct herds and diets and skin. Ankylosaurus did not know that its armor would become an image of prehistoric defense. They were living animals inside a functioning world. The Hell Creek landscape was a warm, humid coastal plain in many reconstructions, with rivers flowing through forests and wetlands toward a nearby sea or low coastal regions. The exact local conditions varied from place to place and through time. Some areas were wetter, some better drained. There were channels, levees, flood basins, ponds, and vegetated overbank deposits. Plants included conifers, ferns, horsetails, palms and palm-like forms, flowering plants, and other groups adapted to lowland environments. A modern visitor might recognize parts of the scene, but not the whole. There would be trees, shade, water, mud, rotting leaves, insects, and the smell of wet ground. There would be birds, because birds are dinosaurs and had already diversified in Cretaceous ecosystems. There would be mammals, small and mostly unobtrusive. But the large animals would change everything. The weight in the mud would be different. The spacing of tracks would be different. The broken branches would be higher, heavier, and made by bodies no human landscape has had to accommodate. Edmontosaurus was one of the major herbivores of this final North American world. It was a large hadrosaur, able to move on all fours while feeding and on two legs when moving faster. Its skull lacked the tall tubular crests of some earlier hadrosaurs, but its jaws were highly effective. The dental battery allowed it to process tough plant material. Skin impressions from related specimens show that hadrosaurs could preserve detailed scales, sometimes enough to give us a sense of body covering and texture. A hadrosaur footprint is a broad, three-toed impression, often less theatrical than the clawed track of a predator, but just as meaningful. It tells us where weight passed through mud. It can show direction, speed, group movement, and substrate conditions. A trackway preserves a moment when the animal was alive, not a rearranged skeleton after death. The foot pressed down. Sediment held the shape, and time did the rest. Triceratops was another central animal of the final kingdom. It was not rare in many Hell Creek assemblages. Its skulls and bones appear often enough to suggest that it was one of the dominant large herbivores in parts of the ecosystem. The three-horned face, parrot-like beak, massive frill, and heavy body made it one of the most formidable animals in the environment. It was not simply prey waiting for Tyrannosaurus, it was a multi-ton herbivore with a dangerous head. The relationship between Triceratops and Tyrannosaurus has evidence behind it. Tyrannosaur tooth marks occur on ceratopsian bones. Some bones show signs of feeding after death. Others preserve healed injuries that suggest encounters survived during life, though individual cases must be interpreted carefully. The animals shared the same world, and their bodies were shaped in part by the risks and opportunities of that shared existence. A predator could feed on a living Triceratops could make an attack costly. Triceratops skulls also change through growth. Juveniles, subadults, and adults differ in horn orientation, frill shape, and bone texture. This matters because paleontologists must separate species differences from age differences. A young individual can look different enough from an adult to confuse taxonomy if growth is not understood. The fossil record is not just a list of species, it is a population of animals at different ages, and growth can disguise itself as diversity. Tyrannosaurus rex appeared very late in the Cretaceous, within the final few million years. It was not the largest predator for the entire dinosaur age. It was the final form of a long tyrannosaurid history in North America. Its skull was massive, its teeth thick and deeply rooted, its bite among the strongest known for any terrestrial animal. Unlike blade-toothed predators that relied more on slicing, Tyrannosaurus could crush and puncture bone. A Tyrannosaurus tooth is not a slim knife. It is more like a reinforced spike with serrated edges, built to withstand high forces. Broken and shed teeth are common in some deposits because theropods replaced teeth throughout life. Each shed tooth marks a feeding event, a lost weapon, or ordinary wear. When found near bones with matching punctures, it becomes part of a behavioral story. The animal bit, pulled, fed, broke teeth, grew new ones, and continued. The skull of Tyrannosaurus was a whole instrument. Deep jaws, forward-facing eyes, expanded areas for muscle attachment, and a strong neck worked together. Its arms were famously short, but the animal was not incomplete because of them. Evolution does not work toward human expectations of proportion. The reduced arms belong to a body plan where the skull had become dominant. A living Tyrannosaurus would have been balanced not as a monster with missing parts, but as a specialized animal whose center of power sat in the head. The question of whether Tyrannosaurus was predator, scavenger, or both has mostly settled into a more realistic answer. It was almost certainly both, as large carnivores are today. A living predator does not refuse carrion because it has a reputation to maintain. It hunts when it can, scavenges when it can, steals when it can, and avoids unnecessary injury when possible. Tyrannosaurus had the senses, body size, and weaponry for predation, and the digestive opportunity to exploit carcasses. We should be cautious about turning every injury into a battle scene. A tooth mark can come from scavenging. A healed wound can come from a failed attack, a fight with another member of the same species, an accident, or a bite from a different predator. The fossil record is evidence, but evidence needs restraint. What it shows clearly is that these animals interacted physically. They bit, fed, healed, and sometimes survived serious trauma. Ankylosaurus occupied a very different survival strategy. It was low, broad, armored, and heavy, with bony plates embedded in the skin and a tail ending in a large club. Complete skeletons are, but enough is known to show an animal built for defense. The skull was wide, the body was protected. The tail club could deliver force if swung into a predator's leg or body. In the final kingdom, not every herbivore relied on horns, speed, or numbers. Some became difficult to bite safely. Imagine a Tyrannosaurus approaching an adult Ankylosaurus from the wrong angle. The predator has size and bite force, but the prey has armor, a low center of gravity, and a weapon at the end of the tail. A broken leg could be a death sentence for a large predator. Risk matters. Predators do not simply attack every animal they can see. They choose, hesitate, test, retreat, or wait. A defended herbivore survives partly by making the calculation unfavorable. Pachycephalosaurus was stranger, at least to modern eyes. Its domed skull, thickened with bone, has led to long debate about headbutting, flank butting, display, and species recognition. The dome may have served more than one function. The animal itself is mostly known from skull material, with the rest of the body less complete than we would like. Yet even that dome is enough to show that late Cretaceous herbivores were experimenting with social signals beyond horns and frills. The dome of Pachycephalosaurus is a reminder that not all important structures are about predators. Animals compete with members of their own species. They display maturity. They recognize rivals. They communicate strength or identity without necessarily killing each other. The fossil skull is silent, but its shape belongs to behavior. It asks us to imagine an animal not frozen in a museum pose, but turning its head toward another of its kind. Thescelosaurus, smaller and less famous than its neighbors. may have been one of the more common small herbivores in parts of the final ecosystems. It was built close to the ground compared with giant hadrosaurs and ceratopsians, a sturdy ornithischian feeding in understory habitats. Animals like this matter because ecosystems are not made only of icons. The background species carry energy through the food web, feed smaller predators, disturb vegetation, dig, browse, and leave tracks that fill the spaces between the giants. Small mammals lived in these environments too. They were not the dominant large animals, but they were diverse in their own scales, occupying insect-eating, omnivorous, and plant-eating roles. Some climbed, some burrowed, some moved at night. They lived under the feet of dinosaurs, but not outside evolution's attention. When the extinction came, mammalian lineages would survive and eventually expand, but in the Cretaceous, they were part of a dinosaur-dominated world rather than its replacement. Crocodilians, turtles, fish, amphibians, lizards, snakes, birds, pterosaurs, insects, and plants completed the living fabric. A Hell Creek River was not a backdrop painted behind Tyrannosaurus. It was an ecosystem in its own right. Gar-like fish moved in water. Turtles basked or buried themselves in mud. Crocodilian relatives waded near banks. Insects fed on leaves, wood, dung, and carcasses. Fungi broke down dead material. Plants stabilized sediment. The dinosaurs were the most visible animals, but not the only ones making the world work. A bone bed can flatten that complexity. Many animals end up together after transport, flood, drought, or repeated accumulation. The deposit may look like a single catastrophe even when it formed over time. Paleontologists read orientation, abrasion, breakage, sediment grain size, and association to understand how the bones arrived. A jumble of fossils is not chaos if you learn the language of water and decay. Farther south, in the latest Cretaceous of what is now Texas and surrounding regions, the final American dinosaur kingdom included one of its last great sauropods. Alamosaurus was a titanosaur, part of a group that remained especially successful in the southern hemisphere, but also returned or persisted in parts of North America near the end. Its presence means that long-necked giants had not vanished entirely from the continent. In the south, under different conditions, the sauropod body plan still worked. Alamosaurus restores a scale often missing from the familiar Hell Creek picture. The final North American dinosaur world was not only Tyrannosaurus and Triceratops on northern floodplains. In southern landscapes, a giant sauropod could move through warm habitats, feeding high and low, its steps pressing deep into soft ground. The animal belonged to the same final chapter, but to a different province of that chapter. Cretaceous America was wide enough to hold more than one ending. Big Bend and the surrounding region preserve a complex late Cretaceous world of rivers, floodplains, volcanic influence, and coastal settings near the margin of the continent. Alongside dinosaurs, the region is famous for giant pterosaurs such as Quetzalcoatlus, whose wingspan exceeded that of any living bird. A pterosaur standing on the ground in such a place would not have been merely a seabird analog. It was a large, walking, flying reptile sharing space with dinosaurs in a landscape that mixed open areas, waterways, and forested patches. Quetzalcoatlus changes the sky. A flying animal that large does not pass unnoticed. Its shadow, its landing, its movement on the ground, all would have altered the behavior of smaller animals nearby. It may have fed by stalking on land, taking small vertebrates and other prey, though details remain debated. Whatever its precise habits, its presence shows that the last dinosaur kingdom had more than giants on the ground. The air above it still belonged to reptiles as well as birds. The retreat of the Seaway did not make the continent modern. It left behind sediments, coal-forming swamps, coastal plains, and reorganized river systems. It also changed the possibilities for dispersal. As barriers shifted, animals may have moved into new ranges or encountered populations previously separated. The last million years of the Cretaceous were not a static waiting room before extinction. They were ecologically active, with communities continuing to respond to geography, climate, and evolution. Whether non-avian dinosaurs were declining before the asteroid remains one of the major questions in paleontology. Some studies suggest diversity was falling in certain groups or regions before the end. Others find that at least some latest Cretaceous ecosystems remained rich and stable close to the boundary. The answer may not be the same everywhere. North America, with its strong but uneven record, plays a central role in that debate. The safest statement is that the asteroid struck living ecosystems, not a world already emptied of dinosaurs. The boundary itself is a physical thing in some places. A thin layer enriched in iridium, shocked minerals, spherules, and other signs of impact fallout marks the transition from the Cretaceous to the Paleogene. Below it are the last non-avian dinosaur-bearing rocks. Above it, their bones vanish. The layer is not metaphorical. It can be sampled, measured, and traced. It is one of the most consequential horizons in the history of life. The asteroid that struck near what is now the Yucatan Peninsula released energy beyond human experience. It blasted material into the atmosphere, ignited fires in some regions, triggered tsunamis, and sent dust and aerosols around the globe. Sunlight was reduced. Photosynthesis faltered. Food webs collapsed from the bottom upward. The destruction was not only the immediate violence of impact, it was the climatic aftermath, the failure of plants, the starvation of herbivores, and the predators that followed them into collapse. In North America, the final dinosaur kingdom lay close enough to the impact site to experience severe consequences. Coastal regions around the Gulf would have been devastated. Inland environments faced darkness, cooling, acid rain, fires, and the breakdown of seasonal expectations. A Triceratops did not need to understand the sky had changed. It only needed the plants to stop growing normally. An Edmontosaurus did not need to see the crater. It only needed the food web to fail. Extinction often sounds clean when reduced to a date. 66 million years ago. The end of the Cretaceous, the disappearance of non-avian dinosaurs. But for living animals, it would have been confusion, hunger, smoke, darkness, cold, contaminated water, and the loss of patterns that had guided life for generations. Nests failed. Juveniles weakened. Herds moved through altered landscapes. Predators found carcasses at first, then fewer living animals, then fewer carcasses worth finding. Birds survived, but not all birds. Mammals survived, but not all mammals. Crocodilians, turtles, amphibians, fish, insects, plants, and many other groups passed through the crisis unevenly. Survival depended on body size, diet, habitat, reproduction, shelter, and chance. Animals that could eat seeds, detritus, carrion, aquatic food, or stored resources had advantages in some settings. Large land animals with high food demands were especially vulnerable when plant productivity crashed. It is tempting to make extinction moral, to say the dinosaurs were obsolete or doomed by some weakness. The evidence does not require that. Many were successful until the end. They had endured climate shifts, sea level changes, volcanic episodes, predator turnovers, plant revolutions, and continental rearrangements. Their final disappearance was not a failure of being dinosaurs. It was the result of a global catastrophe severe enough to break ecosystems that had functioned for millions of years. The non-avian dinosaurs vanished, but Dinosauria did not. Birds carried the lineage forward. Every living bird is part of the dinosaur story, not a symbol placed beside it. Their survival does not make the extinction less severe, but it changes its. The last dinosaur kingdom in America ended for Tyrannosaurus and Triceratops, for Edmontosaurus and Ankylosaurus, for the ground-dwelling giants and small-bodied non-avian forms. But a branch of theropods crossed the boundary and kept going. A bird on a fence in Montana, a gull over Kansas, a raven in Alaska, a heron standing in a Gulf Coast marsh, all belong to the living continuation of a Mesozoic lineage. Their bodies have changed. Their world has changed. But the bones, feathers, eggs, air sacs, and ancestry carry deep history inside ordinary movement. The dinosaur age did not completely end. It narrowed, passed through fire and darkness, and emerged in a smaller, winged form. After the extinction, the empty roles left by non-avian dinosaurs did not fill instantly. Ecosystems recovered in stages. Fern spikes in some regions show opportunistic plants spreading after devastation. Mammals diversified over time, but the first post-impact world was not immediately the age of large mammals. It was a recovering world, disturbed, simplified, and unstable in many places. The great bodies were gone. The footprints in mud were smaller. The forests had to rebuild. The rocks above the boundary in North America contain a different fauna. The large dinosaur bones stop. Mammals become more prominent through the Paleogene. Plants recover and reorganize. Crocodilians, turtles, fish, and birds continue. The sediment does not care about our categories. It simply records what was buried. To a paleontologist, the boundary is visible because the assemblage changes so sharply. One world below, another world above. Yet the final dinosaur kingdom is not only important because it ended. It matters because it was alive before it ended. Hell Creek and its neighboring formations preserve a functioning ecosystem with abundant animals, plant communities, rivers, and seasonal rhythms. The title of The Last Kingdom should not make it feel like a ghost story from the beginning. For most of its existence, it was not dying. It was living. Return to the tooth in the gray stone. It may have fallen from the mouth of Tyrannosaurus while feeding. It may have broken against bone. It may have been shed normally, replaced by another tooth pushing into position. Around it, the sediment held fragments of leaves, bits of shell, scales, and bones from animals that shared the same floodplain. The tooth does not say apocalypse. It says appetite. It says maintenance. It says a predator was alive. A Triceratops skull emerging from a hillside says something different. It says growth, impact, display, defense, and mass. The frill may be cracked. The horn tips may be worn. The bone surface may show blood vessel texture and remodeling. The skull is too large to be casual. Even broken, it carries the force of the animal that grew. When exposed by erosion, it becomes not a trophy but a shoreline between times, with modern rain uncovering a Cretaceous face. A hadrosaur skin impression says still another thing. It says that under rare conditions, the outside of an animal can touch the fossil record. Scales pressed into sediment, soft tissue decayed, but the pattern remained. Skin is usually lost, and when it survives as texture, it brings the animal down from abstraction. It had surfaces, it caught light, it carried scars, folds, and patterns of growth. It was not only a skeleton waiting for discovery. The last dinosaur kingdom was made from millions of such ordinary realities. Teeth were replaced. Eggs were laid. Rivers flooded. Plants grew. Feathers molted. Juveniles learned roots. Predators failed more often than they succeeded. Carcasses fed insects, crocodilians, mammals, and other dinosaurs. Ash fell from distant eruptions. Sea level shifted. Mud cracked, softened, and was pressed again by feet. This was not a stage built for extinction. It was a world continuing until it could not. The American record is especially powerful because it includes so many connected pieces: the inland sea, the western island continent, the eastern fragments, the polar north, the southern sauropods, the final northern plains, the boundary layer, and the early recovery above it. No single formation tells the whole story. Together, they show a continent in transformation across nearly 80 million years, ending in one of the most studied extinction events in Earth history. When people imagine Cretaceous America, they often compress it into one scene: Tyrannosaurus facing Triceratops under a storm-dark sky. That scene is not wrong as an image, but it is too small as a world. It leaves out the seaway full of mosasaurs, the Utah floodplains with ornate ceratopsians, the Alberta bonebeds, the New Jersey greensands, the Alaskan polar forests, the Texas giants, the eggshell, the plant fossils, the ash beds, the turtle shells, and the quiet work of rivers. The real kingdom is larger than the icons. It includes a ceratopsian horn weathering out of sandstone in Utah, a hadrosaur nest in Montana, a mosasaur jaw in Kansas chalk, a nodosaur plate from the eastern coastal plain, a tyrannosaur tooth from a northern floodplain, and a sauropod vertebra from the south. Each piece belongs to a different room in the same immense house. The house is gone, but its foundations are still in the rock. To follow those foundations more closely, start again in the rocks older than the final kingdom, where the American Cretaceous was still finding its shape. The early Cretaceous record often feels transitional because it is exactly that. The old Jurassic giants had not vanished everywhere, but the balance of power was changing. Sauropods remained in several regions, sometimes at extraordinary sizes, while iguanodontians expanded and armored dinosaurs persisted. Predators such as Acrocanthosaurus show that large theropods still came from lineages outside the Tyrannosaur family. The continent was not yet the land of horned dinosaurs and duck-billed herds familiar from the end. It was a mixed landscape, carrying old forms forward while making room for new ones. A single sauropod vertebra can make that transition visible. The bone is huge, but much of it is airspace, carved by pneumatic structures connected to the respiratory system. Sauropods had already solved the problem of supporting immense bodies in the Jurassic, and some early Cretaceous North American species continued that inheritance. Sauroposeidon, known from Oklahoma, suggests a very tall animal, perhaps one of the tallest sauropods known from the continent. Its neck bones remind us that even while the final dinosaur kingdom was forming, the long-necked giants had not simply stepped away. Imagine a sauropod moving across an early Cretaceous floodplain. Its head rises above conifers and early flowering shrubs. Its body passes slowly, not because the animal is weak, but because mass has its own pace. Around its feet, smaller animals move through disturbed vegetation. Insects rise. Mud holds deep impressions where the animal crossed wet ground. A predator could follow the trail, but a healthy adult sauropod is not an easy target. Size remains a kind of geography. The plant world around those animals was beginning one of the most important reorganizations in Earth history. Flowering plants started as components of ecosystems, not as immediate rulers of. They appeared in understories, along disturbed banks, in open patches, and in habitats where rapid growth could be useful. Their rise changed insect relationships, seed dispersal, leaf availability, and eventually the structure of forests. For dinosaurs, this did not mean one sudden new diet. It meant a long, uneven widening of paleobotany often speaks in probabilities rather than scenes. A leaf assemblage can suggest climate, but it does not show every plant in the forest. Pollen can travel far from the plant that produced it. Wood can drift before burial. A fossil seed can be separated from its parent by water, yet taken together. Leaves, pollen, wood, seeds, cuticle, and sedimentary setting reveal a Cretaceous land surface changing under the feet of dinosaurs. The food web was being rebuilt from the ground up. The rise of angiosperms also changed the smaller animal world. Insects that fed on leaves, pollen, nectar, wood, and plant tissues found new opportunities. Some insect groups expanded alongside flowering plants, though the timing and details varied. This mattered to dinosaurs indirectly and directly. Small theropods could feed on insects. Birds could exploit insects and seeds. Herbivorous dinosaurs browsed in communities where plant turnover and leaf structure were shifting. The biggest animals were connected to the smallest changes by food. A Cretaceous riverbank would have been one of the places where this new plant world was easiest to see. Disturbed ground favors fast colonizers. Floods tear open space. Sediment bars form and vanish. Young plants grow where sunlight reaches the ground. Along such margins, flowering plants could establish themselves among ferns, horsetails, conifers, and cycads. A hadrosauroid feeding there would not be walking through a modern garden, but it would be encountering a botanical world less Jurassic than the one its ancestors knew. Early relatives of hadrosaurs grew increasingly important in this changing vegetation. The ability to crop and process plants effectively became a major advantage. Iguanodontians and hadrosauroids evolved more complex jaws and teeth, and later hadrosaurs would take this much further with true dental batteries. This trend is easy to overlook because skulls can seem less dramatic than horns or claws, but a jaw that chews efficiently can reshape ecosystems. It lets an animal turn tough plants into growth, muscle, eggs, and offspring. Herbivore success is never only about defense, it is also about digestion. A large plant eater has to gather enough food, process it efficiently, avoid poisoning from plant chemicals, and keep moving through habitats where resources change with seasons and disturbance. Cretaceous herbivores evolved different answers. Sauropods relied on reach and massive fermentation chambers. Hadrosaurs relied increasingly on chewing power. Ceratopsians used beaks, shearing teeth, and strong jaws. Ankylosaurs used broad guts and low browsing strategies. The final kingdom contained all of these inherited solutions. As the period advanced, the inland sea pushed farther into the continent. Shorelines migrated across areas that are now far from any ocean. In one interval, a place could be coastal plain. Later it could be shallow sea. Later still, it could become land again as the seaway withdrew. This constant movement created stacked records of terrestrial, coastal, and marine environments. A cliff can contain the story of a shoreline walking back and forth across the same region for millions of years. The seaway was shallow compared with the open ocean, but it was vast enough to divide the continent and alter climate. Warm water covered the interior, storms moved over it. Marine life occupied its depths and margins. Rivers delivered sediment from the rising west. In places, low oxygen near the bottom slowed decay, helping preserve the animals that sank there. This is why the American interior holds chalks, shales, ammonites, fish, mosasaurs, plesiosaurs, and the ghost of an ocean where the middle of the continent now stands exposed. Mosasaurs were among the great marine success stories of the late Cretaceous. They were not dinosaurs. They were marine lizards, relatives of snakes and monitor lizards in a broad sense, adapted over time to life in water. Their limbs became paddles, their tails became powerful swimming organs, and their jaws carried teeth suited to different prey. Some species hunted fish and squid, others could take larger prey. In the seaway, they filled roles that whales and large sharks would occupy in later seas. A mosasaur jaw from Kansas chalk can be longer than a human body. Its teeth are not the teeth of a land predator. They belong to an animal moving through water, turning with its body and tail, closing on prey in a sea where visibility, depth, and currents shaped every attack. Above it, pterosaurs crossed the air. Below it, ammonites drifted or swam, shells coiled in patterns older than the dinosaurs themselves. The kingdom on land had an ocean for a neighbor. Plesiosaurs brought a different shape to the seaway. Long-necked forms such as Elasmosaurus carried small heads far from the body, with flippers used for underwater flight. Their anatomy looks strange because it was a different solution to marine hunting. Rather than speed alone, a long neck may have allowed a predator to approach prey with the bulk of the body farther away, though exactly how these animals fed remains a subject of study. The fossil record gives the shape. Behavior must be reconstructed cautiously. Marine reptiles can distract from the title if they take over the story, but in Cretaceous America, they cannot be ignored. The inland sea was the reason Laramidia and Appalachia became separate worlds. It controlled shorelines, sediments, climate, and migration. Its animals died in rocks that now help date and correlate nearby terrestrial deposits. Even the land dinosaurs were living in a geography defined by water. On the western side, Laramidia became long and narrow enough that regional differences could matter. Mountain systems to the west, the seaway to the east, and shifting climate along latitude created a chain of habitats rather than a broad continuous plain. Rivers flowed eastward. Sediment accumulated in basins. Coastal wetlands alternated with better drained flood. Dinosaurs moved through this corridor, but not all species necessarily ranged from Mexico to Alaska. Some may have been local, others widespread, and the balance likely changed through time. The debate over dinosaur provincialism on Laramidia is not just about names. It affects how we understand evolution on a crowded landmass. If northern and southern regions had distinct dinosaur communities at the same time, then isolation, climate gradients, and habitat preference were producing local faunas. If species were more widespread than once thought, then the continent was more connected biologically. Both possibilities have consequences for how quickly dinosaurs evolved, how they dispersed, and how resilient they were to environmental change. Kaiparowitz, Wawep, Fruitland, Kirtland, Judith River, Two Medicine, Dinosaur Park, Horseshoe Canyon, Lance, Hell Creek, Frenchman, Scholard, Ojo Alamo, Javelina, and other formations are not just names in a stratigraphic list. They are windows at different heights in time and geography. Each preserves a particular environment under particular conditions. Some are older Campanian worlds full of diverse ceratopsians and hadrosaurs. Some are final Maastrichtian worlds closer to the boundary. Some are southern, some northern, some coastal, some more inland. A fossil hunter walking in the Badlands does not see the whole formation at once. They see a slope, a layer, a contact, a color change, a bone fragment. The grand names come later, on maps and in papers. In the field, the work is physical. The sun is high. The clay sticks after rain and cracks when dry. A bone may be protected with plaster. A jacket may weigh more than the person carrying it wants to admit. The last dinosaur kingdom is recovered one burden at a time. Ceratopsians became especially diverse in the late Cretaceous West. Their skulls are so striking that they can overwhelm the rest of the animal, but the skull was only one part of a large herbivore. Behind the horns and frills were strong shoulders, a heavy torso, powerful limbs, and a beak for cropping vegetation. The teeth were arranged for slicing plant material, and the jaws could process food effectively. They were not simply armored heads on bodies. They were successful herbivores with complex feeding systems. Centrosaurines and Chasmosaurines, two major ceratopsid groups, often differed in skull proportions and ornamentation. Centrosaurines tended to have shorter frills and elaborate nasal or frill structures in many species. Chasmosaurines often had longer frills and prominent brow horns, though the variety is wide. These distinctions help paleontologists trace relationships, but they also point to how important visual anatomy became. In some late Cretaceous environments, large herbivores were communicating with bone. The energy cost of growing a massive skull was not trivial. Horns and frills required minerals, blood supply, and growth time. Such structures persisted because they mattered. They could influence mate choice, dominance, species recognition, predator deterrence, or combinations of these. The exact emphasis may have differed among species. A Styracosaurus frill with long spikes does not need the same explanation as a Triceratops brow horn. Evolution reuses themes, not identical answers. For a predator, those skulls changed the geometry of danger. Attacking a ceratopsian from the front could mean encountering horns, a sharp beak, and a body that could push back with enormous force. Attacking from the side or rear might be safer, but living prey turns, moves, and reacts. The fossil record of tooth marks and healed injuries shows that encounters occurred, but survival for both predator and prey depended on judgment as much as weaponry. Hadrosaurs were no less important because they seem less dramatic. In many late Cretaceous communities, duck-billed dinosaurs were among the most abundant large herbivores. Their crests, when present, varied widely. Lambeosaurines carried hollow cranial crests that may have been used for sound production, display, or species recognition. Saurolophines often lacked tall hollow crests, but still had complex skulls and powerful jaws. Together, they formed a major herbivore radiation across the continent. A Parasaurolophus crest is often imagined as a musical instrument, and it may have helped produce resonant sounds. But even without hearing it, the structure speaks of communication. Air moved through passages of bone. The head carried a shape visible at distance. A herd animal benefits from recognition, from signals, from knowing its own kind in a crowded landscape. The crest was not decoration placed on a skeleton for us. It belonged to a living social body. Hadrosaur bone beds can preserve many individuals, sometimes suggesting herding or mass death events, though each site needs its own explanation. Drought, flood, river transport, repeated accumulation, disease, or miring can all create concentrations. The presence of many bones together does not automatically mean a herd died in one moment. But the abundance of hadrosaur remains in many deposits makes clear that these animals were central to late Cretaceous ecosystems. They turned vegetation into the biomass that supported predators and scavengers. Dinosaur abundance in fossil deposits is not the same as abundance in life. Preservation bias affects everything. Large, sturdy bones preserve better than delicate ones. Animals living near rivers are more likely to be buried than animals living in uplands. Some species may seem rare because their preferred habitats did not preserve fossils. Even so, when a formation produces repeated, widespread evidence for certain animals, a pattern emerges. In Hell Creek, Triceratops and Edmontosaurus are not minor background figures. They are major components of the fauna. Pachycephalosaurs and smaller ornithischians fill the picture further. Their fossils are often less complete, especially when skulls dominate the record. Domed heads preserve differently from bodies. Small skeletons are more easily scattered or destroyed. Yet these animals show that herbivore diversity extended below the giant-size classes. Not every plant eater weighed several tons. Some lived closer to the ground, feeding on low vegetation, seeds, fruits, or softer plants when available. Small dinosaur lives are difficult to recover because their bones pass so easily into absence. A tiny theropod tooth can be mistaken for a sliver of dark stone. A juvenile limb bone can break before burial. A small skull can be crushed beyond recognition. But these animals were everywhere in the living ecosystems. They hunted insects, lizards, mammals, hatchlings, and small vertebrates. They nested, displayed, hid, and died in numbers the fossil record only partly admits. Dromaeosaurids and troodontids, the smaller feathered predators of the late Cretaceous, are often known from teeth and fragmentary bones in North American deposits. Some named forms are better supported than others, and some remain debated. But the presence of small, bird-like theropods is clear. They would have occupied roles very different from large tyrannosaurs, moving through understory, along riverbanks, and perhaps into trees or dense cover depending on species and anatomy. Feathers in these animals should not be imagined as identical to the plumage of modern birds in every case. Some feathers were simple filaments, others were more complex. Their functions included insulation, display, brooding, and in certain lineages, flight or gliding. The broader point is that many theropods were not naked reptiles. The dinosaur body, especially among coelurosaurs, had already crossed into a world of plumage, color possibilities, and bird-like growth. Color is rarely preserved directly, but sometimes microscopic structures in exceptional fossils can suggest pigmentation. For most North American dinosaurs, we do not know colors with confidence. That uncertainty should not turn them gray by default. Living animals use color for camouflage, signaling, sexual display, age differences, and species recognition. A ceratopsian frill, a hadrosaur crest, or feathered theropod plumage may have carried visual information now lost. The fossils preserve shape more often than surface. The lost colors are one of the hardest absences to feel. We have the horn, but not the flush of skin over it. We have the crest, but not its pattern. We have the scale impression, but not the way sunlight moved across the animal's side. Museums give us bone because bone survives. The living kingdom had skin, eyes, keratin, feather, dust, blood, and weather on every surface. Skin impressions from hadrosaurs, ceratopsians, tyrannosaurs, and other dinosaurs give brief corrections to the skeletal view. They show scales of different sizes, textures, and arrangements. Some impressions preserve pebbly surfaces, others show larger feature scales. Skin also tells us where soft outlines differed from bare bone. A dinosaur was not a skeleton wrapped tightly in leather. Muscles, fat, cartilage, keratin, and skin change the silhouette. Tyrannosaurus itself has generated debate about the extent of feathers or scales. Close relatives from earlier or different environments show evidence of feathers in some cases, while skin impressions attributed to tyrannosaurids indicate scales on certain body regions. The safest reconstruction may allow for regional variation, age differences, and species differences rather than one simple covering. A large adult Tyrannosaurus in a warm lowland may not have looked like a small feathered relative from a cooler setting. Evolution is specific. The sense organs of dinosaurs are another way to bring them back as animals. Tyrannosaurus had forward-facing eyes and large olfactory regions, suggesting strong depth perception and smell. Hadrosaurs and ceratopsians had sensory worlds shaped by their own needs. The position of eyes, nasal passages, inner ear structures, and brain cavity all provide clues. These animals did not move through a silent, vague landscape. They smelled water, carrion, plants, mates, rivals, smoke, and mud. A Cretaceous dawn on a floodplain would have been noisy, though not with the same sounds as a modern forest. Birds called. Insects moved. Water stirred. Crocodilians or turtles shifted at the bank. Hadrosaurs may have produced low calls, especially crested forms with resonating passages. Ceratopsians may have grunted, bellowed, or made other sounds we cannot reconstruct precisely. Tyrannosaurs breathed through large nasal passages. Sound traveled through humid air and vegetation before any human ear existed to hear it. Smell mattered at the scale of carcasses and rivers. A dead hadrosaur near a channel would draw insects first, then small scavengers, then larger ones if the carcass remained accessible. Tyrannosaurus could have found carrion over distance if its smell was as strong as anatomy suggests. Crocodilians might feed from the water side. Small theropods might take pieces at the edges. Bones would be trampled, scattered, bitten, dried, flooded, and perhaps buried. A carcass is not only death, it is a temporary ecosystem. Beetles, flies, bacteria, fungi, scavenging mammals, turtles, crocodilians, theropods, and the river itself all take part. Tooth marks on bone capture only the hardest participants. Soft tissues vanish. Odor vanishes. The swarm of insects vanishes. What remains may be a chewed femur, a few shed and sediment packed into the cavities where life used to be. Trace fossils add another dimension because they record behavior directly. Tracks, burrows, feeding marks, coprolites, root traces, and borings all show activity, rather than anatomy alone. Dinosaur trackways from Cretaceous North America can reveal walking speeds, group movement, foot posture, and substrate conditions. A track is a fossil of weight and motion. It says the animal was here, alive, pressing down, moving somewhere for reasons the track does not explain. Tracks must be interpreted carefully. A footprint can be distorted by mud consistency, overprinting, erosion, undertracks, and the angle of the foot. The shape preserved in rock is not always the exact shape of the foot. Still, trackways are invaluable because they preserve moments that bones cannot. A skeleton may drift after death. A track stays where the animals. In a continent of shifting rivers and shorelines, footprints are among the most immediate fossils we have. coprolites, fossil dung, can reveal diet, digestion, and ecosystem interactions. Some large coprolites from late Cretaceous deposits contain bone fragments, suggesting production by large carnivores capable of crushing and ingesting bone. Plant-rich coprolites can preserve traces of vegetation. These fossils are not glamorous, but they are direct evidence of feeding and digestion. They show what passed through bodies, not just what bodies looked like. A coprolite is easy to laugh at until you remember what it contains. Meals, bacteria, broken bone. Plant fibers. The chemistry of digestion, a moment when an animal stopped, emptied its gut, and moved on. Millions of years later, that unremarkable act becomes a data point in reconstructing a vanished ecosystem. Deep time preserves strange things without embarrassment. The final kingdom also had parasites, diseases, and injuries. Fossil bones preserve infections, fractures, arthritis, bite wounds, and developmental abnormalities. These pathologies show that dinosaurs lived through pain, healed when they could, and sometimes survived injuries that would have changed their movement or feeding. A healed rib or damaged jaw can reveal resilience. An infected bone can show that survival was not clean or easy. Pathology should not be over-dramatized. A swollen bone does not automatically mean a heroic fight. It may mean infection, stress, age, or an accident. But even modest injuries matter because they make the animal individual. They show that life was not an idealized reconstruction. Dinosaurs slipped, fought, overstrained joints, suffered bites, healed, limped, and continued. Some bones carry the record of years lived after damage. Weather added its own pressure. A warm Cretaceous climate still held storms, floods, dry spells, and seasonal changes. River channels migrated. Flood basins filled and dried. Plants responded to rainfall. Animals followed water and food. A herd of hadrosaurs might move through a wet season landscape of soft banks and abundant growth, then face a drier interval where water concentrated animals and predators near fewer places. Ecosystems breathe with seasons. Drought can make fossil deposits. Animals gather at shrinking water sources. Mud traps the weak. Carcasses accumulate. Predators arrive, and sometimes die too. Later, rain returns and buries what remains. Not every bone bed forms this way, but drought is one of the recurring forces in terrestrial preservation. A dry season can become a layer of death that paleontologists uncover long after the water returned and vanished again. Floods can be just as important. A sudden overbank flood can bury eggs, nests, small animals, plant debris, and carcasses. It can also destroy, scatter, and mix. The difference between preservation and erasure can be a few hours of sediment movement. A nest covered gently may preserve eggshell and embryos. A stronger current may tear the nest apart and carry fragments downstream. The fossil record is made from such uneven accidents. Nests tell us about place fidelity. Some dinosaurs may have returned to nesting grounds repeatedly, choosing substrates and spacing that improved egg survival. Colonial nesting offers protection in numbers, but it also concentrates risk. A flood, drought, predator, or disease can affect many nests at once. The Cretaceous ground held eggs before it held bones, and each egg was a gamble against weather, time, and hunger. Eggshell microstructure helps identify groups and reproductive strategies. Thickness, pore density, and shell layers can indicate gas exchange and nesting environment. Eggs buried in vegetation or sediment need different conditions than eggs exposed in open nests. The embryos inside depended on temperature, moisture, oxygen, and protection. The dinosaur kingdom reproduced through fragile mineral shells, each one containing a future that might never hatch. It is easy to imagine dinosaurs only at full size, because that is how museum halls present them. But every Tyrannosaurus began inside an egg. Every Triceratops skull began as a small growing head. Every Edmontosaurus herd depended on hatchlings surviving long enough to replace adults. The last kingdom was renewed each season through small bodies vulnerable to cold, hunger, trampling, disease, and teeth. Juvenile dinosaurs may have occupied different niches from adults, reducing competition within a species. A young Tyrannosaur, long-legged and lighter, may have hunted smaller, faster prey than a heavy adult specialized for crushing force. This would make a single species into several ecological roles across its lifetime. The same animal lineage could move through the food web as it grew, changing prey, behavior, and risk at each stage. Ontogeny, the process of growth and development, is central to dinosaur interpretation. Without growth series, paleontologists may mistake juveniles for separate species or merge distinct species incorrectly. Bone texture, fusion of skeletal elements, size, proportions, and histology all help determine age. In groups such as ceratopsians and pachycephalosaurs, where skulls change dramatically through life, ontogeny can be especially difficult and important. The final American dinosaur kingdom contained multiple generations living at once. Old animals with worn teeth or healed injuries, prime adults in breeding condition, subadults moving into larger roles, juveniles feeding in safer cover, hatchlings hidden near nests or following adults, depending on species. This age structure rarely appears in one fossil bed, but it existed in life. A living ecosystem is not only species diversity, it is age diversity. The scale of a large dinosaur life is measured not only in length or weight, but in time. A Tyrannosaurus may have taken many years to reach its full size, with rapid adolescent growth. A Triceratops grew its horns and frill through changing stages. A sauropod took years to become too large for most predators. Every giant body was a long investment of food and survival. The extinction ended not only adults, but all those long developmental pathways. Migration is harder to prove, but movement across landscapes is certain. Animals followed food, water, nesting grounds, and seasonal conditions. Isotopes in teeth and bones can sometimes hint at movement or diet. Trackways can show local bonobeds can suggest herd behavior or repeated use of areas. In a narrow landmass like Laramidia, river corridors and coastal plains may have structured how animals moved north, south, east, and west. We should not assume every large herbivore migrated like modern wildebeest or caribou. Some may have stayed within smaller home ranges if food and water were reliable. Others may have moved seasonally across longer distances. Different species, ages, and regions likely varied. The fossil record can suggest movement, but it rarely gives an itinerary. The safest image is not one grand migration, but many patterns of movement layered across the continent. Food plants varied across those routes. A hadrosaur feeding in a wet coastal plain encountered different vegetation from one browsing in a better drained upland or a polar forest. Ceratopsians may have preferred certain plant heights or textures. Ankylosaurs likely fed low, using broad muzzles and strong guts to process vegetation near the ground. Sauropods in the south could browse at multiple heights. Feeding height and jaw mechanics divided plant resources before any human name divided the animals. Niche partitioning is the scientific term, but the idea is simple. Several large herbivores can live together if they do not all use the environment in exactly the same way. They may feed at different heights, prefer different plants, use different habitats, move at different times, or process food differently. The late Cretaceous was crowded with herbivores in some regions, and their coexistence implies ecological separation that bones only partly reveal. Predators also divided the world. A giant tyrannosaur was not competing directly with every small theropod. Juvenile tyrannosaurs may have filled intermediate predatory roles. Dromaeosaurids, troodontids, and other small theropods hunted smaller prey. Crocodilians controlled water edges. Birds and pterosaurs took food from air, water, shore, and land, depending on species. The predatory guild was layered, with danger coming in different sizes. For a small mammal, the shadow of Tyrannosaurus might matter less than the quick movement of a small theropod. For a hatchling hadrosaur, a crocodilian at the water's edge could be more dangerous than a distant adult tyrannosaur. For an adult Triceratops, the main predator was large enough to leave deep punctures in bone. Risk is always relative to body size, habitat, and behavior. The kingdom was full of overlapping fear. Mammals in the late Cretaceous were more diverse than old stereotypes suggest. They were generally small, but not insignificant. Multituberculates, metatherians, eutherians, and other groups occupied different roles. Teeth provide much of the evidence, because small mammal teeth preserve well and carry detailed information about diet and relationships. A tiny molar from a screen-washed sediment sample can be as scientifically valuable as a dinosaur femur. Screenwashing is one of the least cinematic and most important methods in paleontology. Sediment is collected, soaked, washed through mesh, and searched for tiny fossils. Out come teeth, scales, bones, shells, seeds, and fragments too small to notice in the field. Through screenwashing, the ecosystem fills with small lives. The last kingdom stops being only a parade of giants and becomes a community of animals that could fit in a palm. Plants, too, are recovered through patient work. Pollen grains, spores, leaf cuticles, wood anatomy, and seeds all provide evidence. Palynology, the study of pollen and spores, can track changes through the boundary and across formations. Because pollen is produced in huge quantities and preserves well under the right conditions, it can reveal plant communities even when leaves are rare. A microscope becomes a landscape tool. At the end Cretaceous boundary, plant records in some regions show major disruption. Ferns often appear prominently in early recovery layers, a pattern sometimes called a fern spike. Ferns are good colonizers after disturbance because they disperse by spores and can occupy open ground quickly. This does not mean the entire world became ferns, but it does show that plant communities were heavily disturbed in many places after the impact. Before that disruption, Cretaceous forests and wetlands stored carbon, built soils, stabilized banks, and fed herbivores. Coal seams in some late Cretaceous deposits record peat-forming environments where plant material accumulated in wet, low-oxygen conditions. These were not empty swamps. They were productive ecosystems, dense with roots, insects, amphibians, turtles, crocodilians, small mammals, birds, and dinosaurs moving along firmer margins. A coal seam is a forest transformed by pressure and time. The leaves are gone as leaves. The trunks are gone as trunks. But the carbon remains, compressed from plants that grew under Cretaceous light. Nearby, a dinosaur bone may lie in sandstone from a river channel. Together, the coal and bones say that life was producing more organic matter than decay could, and that sediment was burying it layer by layer. The shorelines of the Western Interior Seaway also preserved brackish environments where freshwater and saltwater mixed. These were complex habitats, rich but unstable. Salinity changed with tides, storms, river discharge, and sea level movement. Animals living there had to tolerate variation. Fossils from such settings can mix marine and terrestrial signals, creating assemblages where shark teeth, shells, crocodilian bones, turtle remains, and dinosaur fragments appear near each other. Mixed deposits can be difficult to interpret. A dinosaur bone near marine fossils does not mean the dinosaur lived in the sea. It may have washed in from a river, floated as a carcass, or been transported as an isolated bone. The surrounding sediment, abrasion, associated fossils, and taphonomy help determine what happened. Paleontology is often the art of not jumping too quickly from proximity to behavior. Taphonomy, the study of what happens from death to discovery, underlies every fossil story. An animal dies. Scavengers feed. Weather cracks bone. Water moves remains. Sediment buries them. Minerals infiltrate. Pressure compacts. Erosion exposes. A person finds. At each step, information is lost, altered, or occasionally preserved. The fossil is not the animal directly. It is the result of a long chain of events that began after the animal stopped living. That chain can be violent or gentle. A carcass torn apart in a river may leave scattered bones with abrasion and bite marks. An animal buried rapidly in a channel may preserve articulated limbs. A footprint baked and buried at the right time may hold the shape of toes. A nest covered by fine sediment may retain eggshell. Each fossil has two histories: the life of the organism and the afterlife of its remains. Museums often hide the afterlife because the finished skeleton looks clean. In the field, fossils are messy. They are broken, heavy, fragile, embedded in rock, and difficult to remove. Plaster jackets protect them. Tools separate bone from matrix. Preparators spend months or years exposing surfaces grain by grain. A mounted dinosaur is the result of geology, field labor, preparation, anatomy, comparison, and reconstruction. The animal becomes visible through human patience. A quarry map is a kind of biography. It marks where each bone lay, its orientation, its depth, its relationship to other bones. A femur here, a rib there, a tooth nearby, a layer change below. Without that map, the skeleton loses context. With it, paleontologists can ask whether the body was articulated, transported, scavenged, or disturbed. The map preserves the fossil's final position before removal, the last arrangement made by water, decay, and sediment. Cretaceous America also exists in public imagination because of early American fossil history. The 19th and early 20th centuries turned Western dinosaurs into scientific and cultural icons. Expeditions, rivalries, museum displays, and new species made the American West seem like the central theater of dinosaur discovery. That history produced important science, but it also shaped which animals became famous. Tyrannosaurus and Triceratops are biological animals, but they are also cultural fossils. Scientific understanding has changed enormously since those early displays. Dinosaurs once reconstructed as tail-dragging reptiles are now understood as active animals with tails held off the ground. Many theropods are now known or inferred to have feathers. Growth, behavior, biomechanics, and ecology are studied with methods unavailable to early paleontologists. The fossils did not change. The questions did. Each generation returns to the bones with better tools and different assumptions. Computed tomography allows researchers to look inside skulls without destroying them, revealing braincase structures, inner ears, sinuses, and replacement teeth. Histology reveals growth rates through thin sections of bone. Isotopy analysis can suggest diet, temperature, or movement under certain conditions. Phylogenetic analysis tests relationships. Geochemical dating constrains time. The Last Kingdom is not only being dug from hillsides, it is being read through scanners, microscopes, and statistical models. None of these tools removes uncertainty. They refine it. A CT scan can show anatomy clearly, but behavior still requires inference. A bone slice can show growth, but not every individual grew the same way. Isotopes can suggest patterns, but diagenesis can alter signals. Science advances by narrowing possibilities, testing explanations, and admitting where the evidence stops. That restraint is part of what makes the reconstructed world trustworthy. The final million years before the boundary are especially important because they ask whether dinosaur ecosystems were robust or already fragile. In the northern Great Plains, the Hell Creek record has been used to argue for persistence of dinosaur diversity close to the boundary, though debates continue about sampling, dating, and regional patterns. In the south, latest Cretaceous records from New Mexico and Texas add evidence that distinct faunas survived near the end. The Last Kingdom was not identical everywhere. The phrase "thriving until the asteroid" can be too simple if applied globally without nuance. Some groups may have been declining in some regions. Sea level changes and habitat loss may have affected certain dinosaurs before the impact. The fossil record is uneven near the boundary, and different methods can produce different patterns. But the evidence does not support an empty continent waiting for extinction. Large dinosaurs remained part of living ecosystems very close to the end. In Hell Creek, the fine details of the uppermost layers matter. Fossils occur up toward the boundary in multiple studies, though the highest few meters can be complicated by sedimentary changes and preservation. A lack of fossils in a particular layer may reflect fewer channel deposits rather than biological absence. This distinction matters. Rocks can go quiet for geological reasons even when animals still lived nearby. Silence in stone has to be interpreted, not simply accepted. The asteroid did not strike a vacant stage. It struck rivers with turtles in them, forests with leaves on them, nests with eggs in them, herds with juveniles in them, and predators with teeth still being replaced in their jaws. The impact ended ongoing lives. That is why the boundary has such weight. It interrupts a sentence that was still being written. The Chicxulub impact was geographically close to North America compared with many other continents, especially to the Gulf Coast and southern regions. Tsunamis, earthquakes, ejecta fallout, thermal radiation, and atmospheric effects would have varied by distance and local conditions. The immediate devastation near the Gulf would have been extreme. Farther inland, the global effects of darkness, cooling, acidification, and food web collapse became decisive. The catastrophe had both local violence and planetary reach. In the hours after impact, material thrown into the atmosphere re-entered, heating the sky in some models enough to ignite fires across wide areas, though the extent and pattern are still studied. Dust and aerosols reduced sunlight. Sulfur from target rocks may have contributed to severe cooling and acid rain. Plants that depended on sunlight faltered. Herbivores lost food. Carnivores lost prey. Aquatic and detritus-based systems had different chances depending on local buffering. Freshwater ecosystems may have offered refuges for some animals, because food chains based partly on detritus could persist when green plant productivity crashed. Crocodilians, turtles, fish, amphibians, and some small animals survived, in part because their ecologies allowed them to endure scarcity, shelter in water or mud, slow metabolism, or exploit food sources unavailable to large dinosaurs. Survival was not about being advanced, it was about fitting the crisis. Body size mattered. Large land animals require large and regular food supplies. They take longer to mature. Their populations may recover slowly. When plant growth collapses and juveniles fail, large herbivores are vulnerable. Large predators dependent on those herbivores follow. Small animals with flexible diets, sheltering behavior, rapid reproduction, or aquatic access had better odds. This helps explain why the non-avian dinosaurs disappeared, while some birds, mammals, reptiles, amphibians, fish, and invertebrates survived. But survival was still selective within those groups. Many birds vanished. Many mammals vanished. Marine ecosystems suffered heavily. Ammonites disappeared. Mosasaurs and plesiosaurs vanished. The impact did not simply remove dinosaurs and leave everything else untouched. It reshaped the biosphere. The reason non-avian dinosaurs stand out is partly because they were the dominant large animals on land, and after the boundary, that dominance was gone. The first generations after the impact inherited a thinned world. Forests were damaged, food webs simplified. The animals that survived lived among absences. No horned faces moved through the floodplains. No tyrannosaur tracks pressed into river mud. No hadrosaur herds fed along channels. The sounds changed. The ground changed. Even the fear in the landscape changed because the largest bodies were missing. Over millions of years, mammals expanded into roles left open, but that expansion should not make them seem like destined replacements. They were survivors taking opportunities in a world radically altered by catastrophe. Evolution does not prepare a crown for the next group in line. It leaves spaces, and lineages that survive may radiate into them. The Cenozoic began not with triumph, but with recovery. Birds carried dinosaurs into that recovery. Their survival likely depended on traits that varied among lineages: small size, flight, beaks, seed-eating, aquatic habits, nesting strategies, or ecological flexibility. The exact reasons certain bird lineages passed through while others died remain studied, but the result is visible outside the window. The living dinosaur record is not hidden in a museum. It moves in parks, fields, cities, wetlands, deserts, and coasts. This continuation changes the final image of Cretaceous America. The non-avian kingdom ended, but not every dinosaur lineage ended. The branch that survived was not the largest, not the most armored, not the strongest biting. It was a set of birds, small enough and adaptable enough to cross a boundary that giants could not. From them came the birds of the Cenozoic, filling skies that pterosaurs no longer occupied. A bird footprint in modern mud is not the same as a hadrosaur track, but it is a distant echo of the same larger story. 3 toes press down. Weight shifts. The foot lifts. The mark may dry, crack, and vanish with the next rain. Usually, it leaves no fossil. But for a moment, a living dinosaur writes itself on the surface of the Earth. The American Cretaceous also reminds us that continents are temporary arrangements. The seaway that once divided North America is gone. The Rocky Mountains continued rising and eroding. Rivers cut through old sediments. Badlands formed where softer rocks were exposed. Glaciers, weather, vegetation, and human activity changed the surface. The fossil beds we search now are erosional accidents, places where deep time has been brought close enough to touch. A formation is not an ancient landscape preserved whole. It is a body of rock made from sediment deposited in particular environments across time. The Hell Creek Formation, for example, does not represent one afternoon or one forest. It represents many channels, floodplains, soils, ponds, and events stacked and spread through a region. When we speak of Hell Creek as a world, we simplify. The real formation contains many worlds layered together. That simplification is useful if we remember its limits. A reconstruction can place a Tyrannosaurus near a Triceratops, and in a broad sense the animals overlapped, but the exact place, season, age, and local habitat matter. Fossils are precise in some ways and broad in others. They can tell us an animal lived in a formation, but not always whether 2 individuals saw each other. They can show coexistence, not every encounter. The same caution applies to behavior. We can infer that Tyrannosaurus fed on large dinosaurs because of tooth marks, tooth shape, jaw mechanics, and coprolites with bone. We can infer that hadrosaurs processed plants effectively because of dental batteries and wear surfaces. We can infer that ceratopsians used horns and frills in social display or defense because of anatomy, growth, injuries, and comparison with living animals. But we should leave room for what bones cannot show. What bones cannot show is often the texture of daily life, the exact smell of a floodplain after heat, the pattern of mosquitoes above standing water, the response of a herd to distant thunder, the color of a tyrannosaur's eye, the sound of a young hadrosaur, the posture of a resting triceratops under shade, the way an ankylosaurus chose a path through brush. These details existed, but most are beyond recovery. Still, absence does not make imagination useless. It only makes it responsible. A good reconstruction begins with evidence and moves outward carefully. It does not fill every gap with drama. It lets some things remain uncertain. The Cretaceous becomes more powerful when it feels like a real ecosystem with limits to our knowledge, not a fantasy where every blank space is painted with certainty. The final kingdom also had geography at scales smaller than continents. A river bend could shape the lives of animals for years. A nesting ground could matter across generations. A patch of higher ground could remain dry during floods and become a refuge. A dead tree could host insects, fungi, and small vertebrates. A pond could preserve leaves and fish. A game trail could become a trackway if conditions aligned. Landscapes are made of local decisions by water, plants, and animals. Consider an oxbow lake on a Hell Creek floodplain. The main river has cut a new path, leaving a crescent of still water behind. Leaves fall into it. Fish live in it while oxygen lasts. Turtles enter and leave. Insects hatch above it. A hadrosaur drinks from the edge. Later, sediment slowly fills the basin. Fine mud covers leaves, bones, and shells. Millions of years later, the lake is a lens of shale in a hillside. Or consider a point bar in a river channel, sand accumulating on the inside of a bend. Tracks mark the damp surface. A storm raises the river. Sand covers the impressions. Later flow cuts through part of the deposit, destroying some tracks and preserving others as undertracks. The resulting fossil surface is partial, distorted, and invaluable. It does not show a full journey. It shows a few steps that escaped erasure. Soil horizons, called paleosols when preserved in the rock record, reveal periods when sediment surfaces were stable long enough for soil to form. Roots penetrated them. Minerals changed. Burrows cut through them. Carbonate nodules or other features may develop depending on climate and drainage. Paleosols help reconstruct rainfall, vegetation, floodplain stability, and time between depositional events. They are the ground the dinosaurs actually walked on, altered into stone. In some Cretaceous deposits, root traces run through layers near dinosaur bones. This means plants grew there before or after burial, sometimes disturbing remains. Roots can break bone, stain sediment, and alter preservation. The fossil record is not sealed away from later life immediately. It can be modified by plants, groundwater, microbes, pressure, and erosion long after the animal dies. Even fossils have ecosystems after death. Erosion is the final editor. Without erosion, many fossils would remain buried forever. With too much erosion, they turn to powder before anyone sees them. The best discoveries happen in a narrow window between exposure and destruction. A skull may weather from a slope for one season, perhaps a few years. If found in time, it enters science. If missed, it breaks apart and returns to sediment. Deep time can wait millions of years and then become urgent. This urgency is why field seasons matter. Paleontologists survey after winter, after storms, after fresh erosion. They return to known localities. They watch hillsides change. A place that showed nothing one year may reveal bone the next. The modern climate becomes part of discovery. Rain, wind, freeze, thaw, and heat all continue the work that rivers began in the Cretaceous. The past is not simply found. It is exposed by ongoing geology. There is humility in that. The largest animals on land can become dependent on a small piece of enamel catching sunlight at the right angle. A lineage that lasted millions of years can be known from one partial skull. A formation that preserves thousands of fossils can still hide more than it reveals. The last dinosaur kingdom was enormous in life and selective in memory. The richness of Western North America has sometimes made the rest of the continent feel secondary. But Cretaceous America was broader than the Badlands. Mexico preserves important dinosaurs from southern Laramidia and beyond. Canada preserves northern faunas. The Gulf Coast records southern and eastern environments. The Atlantic coastal plain preserves pieces of Appalachia. Alaska preserves polar life. Each region adds a different correction to the familiar story. In Mexico, late Cretaceous dinosaurs include hadrosaurs, ceratopsians, tyrannosaurs or tyrannosauroids, ankylosaurs, and other groups, though the record varies by region and interval. These fossils extend the picture of Laramidia southward, showing that the western landmass was not only an Alberta to Montana story. Dinosaurs moved and evolved along a long latitudinal gradient, with climates and habitats changing across distance. Northern Canada and Alaska extend the story in the other direction. The Cretaceous Arctic was warmer than today, but it was still a place of seasonal light extremes. The presence of dinosaurs there challenges older assumptions that dinosaurs required uniformly warm, low-latitude environments. It also supports the broader view of many dinosaurs as physiologically active animals capable of handling conditions once thought unsuitable for them. The continent, then, held dinosaurs from the southern warm lowlands to the polar forests. It held marine reptiles in its interior sea and flying reptiles above its southern plains. It held tiny mammals in leaf litter and giant herbivores breaking branches. It held predators no larger than birds and predators with skulls longer than a person is tall. This range is what makes the last kingdom a kingdom, not any single animal. Tyrannosaurus dominates public imagination partly because it arrived at the end, and endings sharpen memory. But if you look across the Cretaceous, the tyrant king is only the last member of a changing predatory dynasty. Earlier tyrannosauroids were smaller and often overshadowed by other large theropods. Through time, tyrannosaurids became larger, more robust, and more specialized. By the final Maastrichtian, they had become the apex predators of Western North America. This rise involved more than size. Tyrannosaurids developed strong skulls, thick teeth, binocular vision, powerful hind limbs, and sensory systems suited to large predation and scavenging. Juveniles likely differed ecologically from adults. Growth patterns show rapid mass increase during adolescence in some tyrannosaurids. Their success was not a single trait. It was a suite of anatomical, physiological, and ecological features aligned with the prey communities around them. Triceratops also dominates because it was late, large, and abundant. But it too was the final expression of a longer ceratopsian history that began with small earlier relatives in Asia and passed through many North American forms. By the time Triceratops appeared, horned dinosaurs had been experimenting with skull architecture for tens of millions of years. The familiar three-horned face is only the last American version of that broader evolution. A Triceratops bone bed is rare compared with isolated skulls and skeletons, and this has raised questions about its social behavior. Did it live mostly alone, in small groups, or in larger gatherings at times? The evidence is mixed and may vary by age or circumstance. Modern animals do not always choose one social pattern for life. They gather, disperse, pair, compete, and tolerate others depending on season and pressure. Triceratops may have been equally flexible. Edmontosaurus, in contrast, is often imagined as more clearly herd-forming, though again, details depend on evidence. Large hadrosaur bone beds and trackways suggest group behavior in many hadrosaurs. Herding offers advantages against predators, helps juveniles, and supports movement across landscapes. But it also concentrates food demands and disease risk. A herd is not just safety, it is a moving pressure on vegetation and water. When a herd of large herbivores moves through wet ground, it changes the ground. Tracks overlap. Plants are trampled. Banks collapse. Dung feeds insects. Smaller animals follow disturbed paths. Predators follow scent and opportunity. The herd is not merely passing through the environment, it is modifying it. Dinosaurs were ecosystem engineers at body sizes that modern North America no longer contains. Ceratopsians also engineered their habitats through feeding and movement. Beaks clipped vegetation. Heavy bodies opened paths. Horns and frills may have broken branches during movement or combat. Nesting, wallowing, trampling, and carcass deposition all affected soils and plant communities. A landscape with multi-ton herbivores is physically different from one without them. After the extinction, the absence of such animals would have changed vegetation patterns as well as food webs. The end of the dinosaurs was not only the removal of species names, it was the removal of weight. No more three-toed hadrosaur paths across soft banks. No more horned skulls pushing through brush. No more giant tails swinging over low plants. No more sauropod steps in southern mud. The ground itself lost a kind of pressure it had known for more than 150 million years. Before that loss, the kingdom was still renewing. Eggs were still laid in the final years. Teeth were still replaced. Juveniles still grew. Plants still flowered. Rivers still shifted. The fact that extinction was coming does not mean the animals were living in a prelude. The idea of an ending belongs to us because we know the boundary. They experienced only the present. A Triceratops feeding one season before the impact was not almost extinct to itself. It was hungry, alert, responsive to insects, heat, other animals, and the texture of plants in its beak. A Tyrannosaurus walking a river levee did not carry the meaning of a final predator. It carried mass, hunger, sensory attention, and the memory of routes learned through life. The tragedy is not that they knew. The tragedy is that they did not need to. This is why the last dinosaur kingdom can feel both grand and intimate. Grand because it involved continents, seas, mountains, climate, evolution, and planetary catastrophe. Intimate because every piece of evidence returns to an individual body. A tooth formed in a jaw. A bone healed around an injury. An egg held an embryo. A footprint took the shape of one step. The large story is made from small physical events. The Cretaceous lasted long enough for many beginnings and endings before the final one. Species appeared and disappeared throughout it. The seaway expanded and retreated more than once. Dinosaur communities turned over. Plant communities changed. Predators rose and fell. The final asteroid did not erase a static age. It cut through a moving history. That distinction matters because it keeps the Cretaceous from becoming only a countdown. The first half of the period had its own complete worlds. Acrocanthosaurus hunting under southern skies was not a draft version of Tyrannosaurus. Deinonychus stalking near Edmontosaurus was not a prelude to raptors in popular film. Early flowering plants along a riverbank were not waiting to become modern meadows. Each interval was fully real to the animals living inside it. The final kingdom was the last chapter, not the only chapter. In a museum, time is often compressed by space. A visitor can walk from an early Cretaceous predator to a late Cretaceous herbivore in seconds. The body understands a room, not 70 million years. A careful reconstruction has to stretch that room back into time. It has to put distance between animals that never met and closeness between animals whose fossils lie in the same beds. The rock record is the guide. Even within Hell Creek, time matters. Lower levels and upper levels may differ. Species proportions can shift. Rivers migrate. Local habitats change. A fossil from the base of the formation is not necessarily contemporary with one near the top. The formation preserves a span, not a single instant. When we reconstruct the last ecosystem, we combine evidence while remembering that it moved through time. Stratigraphy gives that movement order. Lower layers are generally older than higher layers, unless disturbed. Ash beds, magnetostratigraphy, fossil correlations, and radiometric dates refine the sequence. Without stratigraphy, fossils become isolated curiosities. With it, they become history. We can ask whether a species appears earlier or later, whether diversity changes upward, whether environments shift, and how close certain animals occur to the boundary. The boundary in some localities is not dramatic to the eye. It may be a thin clay layer, a subtle change in sediment, a line that requires chemical analysis to confirm. Yet within that narrow interval lies the difference between a world with non-avian dinosaurs and a world without them. The scale mismatch is startling. A layer you could cover with a hand represents consequences that reorganize the surface of the planet. That is one reason the Cretaceous-Paleogene boundary has become more than a scientific marker. It is a reminder that life can be abundant and still vulnerable. Success over millions of years does not guarantee survival through every kind of catastrophe. Adaptation works within conditions. When conditions change too abruptly and too globally, even dominant lineages can fail. Still, the lesson should not turn into a simple warning pasted over the past. The dinosaurs were not examples placed there for us. They were animals. Their extinction matters scientifically because it reshaped evolution. and emotionally because the fossil record lets us see enough of their world to feel its loss. But the world did not exist to become a lesson. It existed because life was doing what life does under Cretaceous conditions. The rocks do not mourn. They preserve. Mourning is something we bring when we understand what the preservation means. A skull in sandstone is not sad by itself. It is mineral and shape. But when you know it was once a breathing animal in a living ecosystem, and that its entire kind vanished, the stone becomes heavier. American Badlands are full of this kind of weight. Not just because dinosaurs are large, but because the exposed layers show endings and continuities together. Below one surface, Cretaceous bones. Above it, Paleogene recovery. Around it, modern grasses, sage, fences, roads, and birds. The same hillside can hold three worlds at once: the one that made the fossils, the one that followed them, and the one standing in the wind today. A field worker brushing sediment from bone is not traveling back in time. They are meeting time where erosion has brought it forward. The brush does not reveal a complete animal at once. It reveals a curve, a texture, a surface. The hand slows down. The tool changes. The bone is fragile because it has survived too much to be treated roughly. Discovery is often careful, quiet work. That quietness fits the last kingdom better than constant spectacle. There were violent moments, of course. Predation, storms, floods, impact, fire, but most of the fossil record asks for attention rather than noise. A tooth row, a growth line, a pollen grain, a track surface, a weathered fragment of armor. These are not loud things. They become powerful when placed correctly. The title Cretaceous America, the Last Dinosaur Kingdom, can therefore be read in two ways. It is about the final non-avian dinosaur ecosystems of North America, especially the famous western faunas near the end. But it is also about the long construction of those ecosystems across the entire Cretaceous through changing seas, plants, climates, and lineages. The last kingdom was the outcome of a continent in motion. No animal ruled all of it. Tyrannosaurus ruled some food webs at the end, but not the seaway, not the eastern forests we barely know, not the early Cretaceous, not the southern sauropod landscapes in the same way. Triceratops dominated some herbivore communities, but not every region. Edmontosaurus was abundant in some places, absent in others. The kingdom was shared, divided, regional, and temporary. Its greatness lies in that complexity. A simple kingdom would be easier to describe and less true. The real Cretaceous America had multiple centers: Alberta in the Campanian, Utah in the southern interior, Kansas under the Seaway, Montana and the Dakotas near the end, New Jersey and the Carolinas in fragmentary eastern glimpses, Alaska under polar light, Texas with titanosaurs and giant pterosaurs. Each place carried a different part of the age. In the broad view, the result is not a list of dinosaurs, but the sense of crossing a continent that no longer exists. The routes are made from formations. The landmarks are bones. The weather comes from climate proxies. The animals are reconstructed from anatomy, comparison, and caution. The journey is impossible physically, but the evidence gives it shape. And when the journey returns to the present should look slightly changed. A chalk outcrop in Kansas is no longer just pale rock. A badland slope in Montana is no longer only erosion. A bird lifting from a fence is not just a bird. The continent keeps older versions of itself in pieces, and those pieces are enough to make the modern surface feel thin. The last kingdom is gone, but its remains are not passive. They continue to change science. New species are described. Old species are revised. Dates are refined. Museum collections yield discoveries long after fieldwork ended. A bone collected decades ago can answer a question no one was asking when it was found. The past is not finished as knowledge, even when it is finished as life. Somewhere now, in a drawer, there may be a fragment that will change a range map. In a hillside, there may be a skull still hidden behind a few centimeters of sediment. In a private memory of a field season, there may be a locality waiting to be revisited after erosion. The Cretaceous keeps giving, not generously, but persistently. It releases information at the pace of weather and attention. This is why the physical anchors matter. Tooth, track, leaf, ash, eggshell, shell, bone, each prevents the story from drifting into abstraction. Deep time is too large to hold without objects. A single hadrosaur tooth battery makes plant processing real. A single ceratopsian horn core makes display and defense real. A single bentonite layer makes time real. A single bird outside the window makes survival real. Without those objects, extinction becomes a word. With them, it becomes a series of interrupted bodies. A tyrannosaur tooth that would have been replaced if the animal lived. A nest that would have held another generation if the season held. A plant community that would have fed another herd if sunlight remained. The boundary cut across ordinary processes and made them final. The final kingdom did not end everywhere in exactly the same minute, but geologically it vanished almost at once. Some animals died in the immediate aftermath. Others may have persisted briefly in collapsing habitats, though no credible evidence shows non-avian dinosaurs surviving into the Paleogene. Their ecological world failed. Their fossils stop. Above the boundary, the great terrestrial dinosaurs are absent, and absence becomes one of the strongest signals in the rock. Claims of Paleogene non-avian dinosaurs have appeared from time to time, usually based on reworked fossils. A bone eroded from older Cretaceous rock can be redeposited in younger sediment, making it appear later than it is. Paleontologists examine wear, context, stratigraphy, and dating to distinguish true survival from reworking. So far, the evidence supports extinction at the boundary, with no confirmed non-avian dinosaur lineages crossing it. Birds crossed. That single fact keeps the ending from becoming absolute. The word dinosaur splits at the boundary into the lineages that vanished and the lineage that remained. Non-avian dinosaurs are gone. Avian dinosaurs are alive. The distinction is scientific, but it also changes the mood. The last kingdom ended, yet one part of its ancestry still moves through the air. A crow stepping through snow is not a miniature Tyrannosaurus, but it is kin to the same larger branch of life. Its foot, feathers, wishbone, egg, and breathing system carry history deeper than mammals, deeper than humans, deeper than the grass it walks across. The survivor is ordinary, because survival has had 66 million years to become ordinary. The final American dinosaurs did not become birds. Birds had already existed before them. That is important. The living line was not a transformation of Tyrannosaurus after impact. It was a parallel surviving branch of theropod dinosaurs that had split much earlier. Tyrannosaurus and modern birds share ancestry, but one is not the direct ancestor of the other. Evolution branches. It does not arrange itself in a straight museum hallway. This branching pattern is why paleontology depends on relationships as well as dates. A cladogram is not a timeline by itself. It shows relative relationships, common ancestry, and branching order. Time must be added through fossils and dating. Birds sit within theropod dinosaurs, but the closest non-avian relatives of birds are not the giant tyrannosaurids. They are smaller, feathered Maniraptoran lineages. The family tree is precise in ways popular language often blurs. Popular language also tends to separate land, sea, and air too sharply. In Cretaceous America, these systems touched constantly. Pterosaurs nested or fed on land, but flew over water. Dinosaurs died near rivers and washed toward coasts. Marine sediments preserved terrestrial fragments. Birds moved between trees, shores, and open water. The inland sea shaped weather over land. Ecosystems are porous. The fossil record is full of crossings. A pterosaur bone is hollow and delicate, often crushed or fragmentary, yet when preserved it opens the sky. Pteranodon over the seaway, Quetzalcoatlus over southern land, smaller forms in other settings, all remind us that dinosaurs were not the only large vertebrates in Cretaceous air. Birds were present too, but pterosaurs still held major aerial roles until the boundary. Their extinction removed another Mesozoic presence from the post-impact world. Marine extinctions were severe as well. Ammonites, so abundant and useful for dating Mesozoic marine rocks, disappeared. Mosasaurs vanished. Plesiosaurs vanished. Many plankton groups suffered catastrophic losses. The collapse at sea affected food webs built on microscopic life as much as food webs on land. The end of the last dinosaur kingdom was part of a larger planetary break, not an isolated land event. That larger break is what makes the North American record so valuable. It preserves the last terrestrial dinosaurs close to the impact site, the marine systems of the Seaway and Gulf, the boundary layer, and the early recovery. It allows scientists to compare environments before and after in detail. Few places on Earth offer such a powerful combination of iconic animals and geological context. But the value of the record also brings responsibility. Fossil sites can be damaged by careless collecting, erosion, theft, or commercial removal without context. A fossil taken without location and stratigraphic information loses much of its scientific meaning. The bone remains impressive, but the data around it are gone. Context is part of the fossil. Without it, a piece of the kingdom is silenced. Good paleontology preserves context. Field notes, GPS coordinates, stratigraphic sections, photographs, quarry maps, sediment samples, and careful preparation all become part of the scientific record. The fossil is not only the object in a drawer, it is the object plus its history of discovery and placement in rock. This is how isolated remains become evidence for ecosystems rather than curiosities. The public often meets dinosaurs through replicas and mounted skeletons, which are necessary because original fossils can be too heavy, fragile, incomplete, or valuable to mount. Casts allow museums to show posture and scale while preserving original bones for study. Reconstruction involves choices, especially when skeletons are incomplete. Missing elements may be based on close relatives. Posture may reflect current biomechanical understanding. Displays are scientific arguments made visible. A mounted Tyrannosaurus is therefore both animal and interpretation. The bones give the proportions. The mount gives a pose. The pose changes as science changes. Tails rise. Wrists rotate. Spines shift. Feathers appear on some reconstructions. The museum is not a frozen temple of facts. It is a place where the past is repeatedly adjusted to fit better evidence. The same applies to artwork and film. A Cretaceous America scene can be beautiful and still wrong if it ignores time, place, or anatomy. It can be restrained and powerful if it respects evidence. The goal is not to remove imagination, but to make imagination accountable. A floodplain with the right plants, animals, sediment, and climate can feel more compelling than a generic jungle filled with every famous dinosaur at once. Generic prehistoric jungles are one of the common mistakes. Much of Cretaceous North America was warm and vegetated, but it was not all dense tropical rainforest. There were coastal plains, wetlands, open woodlands, river corridors, uplands, semi-arid intervals in some regions, polar forests, and marine shorelines. The word jungle flattens too much. The real landscapes were varied, and that variety is where many of the interesting ecological questions live. The final Hell Creek environment, for example, included wet lowlands and forests, but also channel belts, levees, and better drained surfaces. It was not one endless swamp. Animals used different parts of it. A turtle might spend its life near water. A Triceratops could feed on firmer floodplain ground. A Tyrannosaurus could move across multiple habitats. A small mammal might live in burrows or dense cover. The ecosystem was organized by microhabitats. Microhabitats are easy to miss at dinosaur scale. A fallen log may matter to insects, lizards, mammals, and young dinosaurs. A rotting stump may hold beetle larvae. A shallow pond may breed amphibians. A patch of flowering shrubs may attract insects and small herbivores. Large dinosaurs pass through such places, but smaller animals live inside them. The kingdom contains worlds within worlds. The body temperature and metabolism of dinosaurs remain complex topics. Many dinosaurs appear to have had elevated metabolic rates compared with typical reptiles, but not all groups were identical. Growth rates, bone tissue, respiratory anatomy, insulation, and activity levels all contribute to the picture. Large body size also stabilizes temperature through thermal inertia. A giant herbivore does not experience heat the same way a small feathered theropod does. The old division between cold-blooded reptiles and warm-blooded mammals does not capture dinosaur biology well. Living animals show a range of metabolic strategies, and extinct animals likely did too. Birds, the living dinosaurs, have high metabolisms. Crocodilians, their closest living relatives outside birds, have different physiology. Non-avian dinosaurs occupied a broad space between and beyond simple categories. Their success across climates suggests flexible and often active biology. Respiration was part of that success. Many theropods and sauropods had air sac systems related to the efficient breathing seen in birds. Pneumatic bones show where air sacs invaded the skeleton. This system helped lighten bodies and move air effectively. It is one of the deep anatomical connections between giant extinct dinosaurs and living birds. A sparrow's breath and a sauropod's vertebra belong to the same larger evolutionary theme. The thought is almost too large for the object. A hollow space inside a fossil bone, filled now with stone or air in a museum, is related to the breathing system that lets birds fly over the modern world. The ancient body and the living sky are connected through anatomy. Cretaceous America did not simply vanish into romance. Some of its engineering survived. The skeletons of large dinosaurs also show how bodies solved mechanical problems. Weight had to pass through hips, knees, ankles, and feet. Muscles had to move limbs without wasting energy. Tails balanced bodies. Necks reached food or carried heads into position. Skulls had to withstand feeding forces. Armor had to protect without making movement impossible. Horns had to be strong enough for use and light enough to grow. Each fossil is a biological engineering solution. Failure is visible too. Stress fractures, arthritis, fused bones, broken ribs, infected wounds. Large bodies are powerful, but they are not invincible. A heavy animal that injures a limb may struggle to feed or escape. A predator with a damaged jaw may starve. A herbivore with worn teeth may decline. Evolution builds systems that work well enough, not systems immune to damage. Teeth are among the most informative fossils because they are abundant, durable, and tied to diet. Theropod teeth differ in shape, serration density, thickness, and curvature. Hadrosaur teeth stack into batteries. Ceratopsian teeth form slicing surfaces. Ankylosaur teeth tend to be small and leaf-shaped. Mammal teeth reveal fine dietary distinctions. A site with many isolated teeth can identify animals even when skeletons are absent. Tooth replacement is especially important. Dinosaurs replaced teeth continuously, unlike mammals with limited tooth generations. This allowed herbivores and carnivores to maintain feeding ability despite wear and breakage. A hadrosaur could grind plants with tooth batteries that renewed from within. A tyrannosaur could lose a tooth in bone and grow another. The ground of Cretaceous America was seeded with discarded feeding tools. Claws tell different stories. A tyrannosaur foot claw supports weight and traction. A dromaeosaur sickle claw suggests gripping, pinning, or slashing functions still debated. A therizinosaur claw from elsewhere shows how strange theropod herbivory could become, though not central to this American final story. An ankylosaur hoof-like foot spreads weight. A hadrosaur hand and foot show movement between quadrupedal feeding and bipedal locomotion. Every extremity is a compromise between motion, feeding, defense, and growth. The hand of Tyrannosaurus, small as it is, was not useless. It had strong bones and claws, though its limited reach constrains possible functions. It may have helped during rising, mating, gripping at close range, or other behaviors difficult to prove. The main point is that small does not mean meaningless. Evolution can reduce a structure and still leave it functional within a narrow role. The hands of earlier or smaller theropods show more obvious grasping. Deinonychus and other Maniraptorans had arms involved in prey capture, balance, display, brooding, or locomotor transitions, depending on lineage. The folding wrist of many theropods is part of the ancestry of the birdwing. A predatory arm becomes, across deep time and many branches, part of the machinery of flight. The Cretaceous contains both hunting hands and wings. A feathered arm around eggs is one of the most intimate images in dinosaur paleontology, known especially from some Asian fossils, but relevant to how we think about theropod reproduction more broadly. Brooding behavior connects body heat, feathers, nests, and parental investment. It turns the fearsome theropod body into something quieter, without making it less predatory. Animals are allowed to be more than one thing. North American evidence for brooding is less spectacular than some deposits elsewhere, but nests, eggs, and reproductive traces still shape the story. Dinosaur reproduction was diverse. Some species likely provided more care than others. Some hatchlings were more developed at birth. Some nests were buried or covered with vegetation. Others may have been more open. The final kingdom reproduced through strategies as varied as the animals themselves. We should not project modern bird behavior wholesale onto all dinosaurs. Birds are living dinosaurs, but they are a specialized surviving branch. Crocodilians are also useful comparisons for nesting and parental care in archosaurs. Between these living relatives and the fossil evidence, paleontologists infer possibilities. The result is not certainty for every species, but a richer range of plausible behaviors than older reconstructions allowed. Social behavior is similar. Bone beds, trackways, nesting colonies, growth series, and display structures can all suggest interactions among individuals, but the exact form of social life is rarely knowable. A herd, a nesting colony, a seasonal gathering, a drought accumulation, and a transported bone bed can look superficially similar if context is ignored. Evidence must be assembled from multiple lines. The restraint can feel disappointing if the desired answer is a clear scene, but restraint protects the wonder. It means that when paleontologists do infer behavior, the inference rests on something. A trackway with many parallel footprints. A nesting horizon with repeated clutches. A healed bite mark. A skull shaped for display. The living moment remains partly hidden, but it is not invented from nothing. The last dinosaur kingdom is therefore a balance between the known and the unreachable. We know the names of many animals. We know some ages, formations, anatomies, diets, and relationships. We know the sea divided the land, that flowering plants rose, that tyrannosaurs became apex predators, that hadrosaurs and ceratopsians became dominant herbivores, that the boundary marks a catastrophic extinction. We do not know every color, sound, route, season, or behavior. That boundary between knowledge and mystery is where the reconstruction holds. Too much certainty makes the past false. Too much vagueness makes it disappear. The fossils ask for a middle distance, close enough to see the tooth serrations, far enough to admit the animal is gone. Even after thousands of fossils, Tyrannosaurus remains partly unknown. Its exact hunting behavior, social interactions, growth variation, and appearance continue to be studied. Triceratops remains debated in details of species, growth, and display. Hadrosaurs continue to reveal new soft tissue and biomechanical information. Ankylosaurus is still frustratingly incomplete compared with its fame. The icons are not solved. They are active scientific subjects. New discoveries often complicate, rather than simplify. A new specimen can show that a feature once thought diagnostic is actually variation with age. A more complete skeleton can revise posture. A better date can move a species into a different interval. A new analysis can change relationships. This is not weakness in science. It is how the picture improves. The last kingdom becomes clearer by being revised. The same process affects formations themselves. Depositional models are updated. Boundaries are refined. Paleoclimate estimates change with new data. Fossil localities are reinterpreted. A bed once thought to represent a swamp may be understood as a flood basin or abandoned channel. A bone concentration may shift from mass death to attritional accumulation. The rocks are constant, but explanations mature. That means any account of Cretaceous America is never the final word. It is a reconstruction from current evidence, written inside an ongoing conversation. The animals are extinct, but the science is not. Somewhere, a graduate student is measuring a tooth. Somewhere, a preparator is exposing a skull. Somewhere, an old field note is being digitized. Somewhere, rain is cutting into a slope that has not shown its fossil yet. If the final kingdom has a center of gravity, it may be the relationship between landscape change and biological response. Seas advanced and retreated. Mountains rose. Plants diversified. Predator guilds turned over. Herbivores developed new feeding systems. Regions separated and reconnected. Then a catastrophe arrived from outside the normal rhythms of Earth systems and broke the continuity. The story is not only who lived, it is how a continent made living possible, then how the planet interrupted it. The asteroid was external in one sense, a body from space striking Earth, but its consequences played out through Earth's own systems: atmosphere, ocean, climate, sediment, fire, darkness, chemistry, and food webs. The end of Cretaceous America was cosmic and terrestrial at the same time. A crater in the Yucatan and a tooth in Montana are connected through the same event. The more we learn, the more the last kingdom becomes both specific and vast. Specific because the animals have names, ranges, bones, and formations. Vast because each name opens into anatomy, behavior, environment, and time. Tyrannosaurus is not just Tyrannosaurus. It is growth, bite mechanics, sensory biology, feeding traces, population questions, and cultural history. Triceratops is not just a horned face. It is ontogeny, abundance, defense, display, and herbivory. Even the smallest fossils widen the view. A mammal tooth says the ground layer was alive. A seed says plants were changing. A fish scale says water held food webs. A turtle shell says slow bodies survived beside giants. A pollen grain says the air carried reproductive dust from plants no human eye ever saw. A dinosaur bone is never alone if the surrounding sediment is read carefully. The final scenes of the Cretaceous, then, should not be imagined only in darkness. Before the darkness came, there was light on water, shade under leaves, heat over mud, and animals doing ordinary things. An Edmontosaurus cropped plants with a mouth full of replacement teeth. A Triceratops pushed through vegetation. A young Tyrannosaur watched movement near a channel. A bird landed on a branch. A turtle slid from a bank. A storm formed beyond the trees. Then, somewhere beyond their sky, an object moved on a path none of them could sense. The animals did not live in suspense. The impact was not part of their world until it entered it. That is one of the most difficult parts of deep time to hold. The future can be enormous and still invisible to the present. When the impact came, it became part of every environment at once. Not equally, not identically, but globally. The final kingdom was no longer separated from the Seaway, Appalachia, Laramidia, the Gulf Coast, or the polar forests by ordinary geography. Atmospheric change connected them. Darkness connected them. Food failure connected them. The continent that had been divided by water became unified by catastrophe. In that sense, the asteroid did what the Seaway had not. The Seaway separated dinosaur worlds for millions of years. The impact ended them together. The western floodplains, southern giants, eastern fragments, polar forests, and marine reptiles all entered the same boundary. The last dinosaur kingdom was regional in life and planetary in death. Afterward, erosion began the long work of revealing and hiding. The bones remained in some places, mineralizing, cracking, being buried deeper, being lifted, being cut by rivers, being exposed by modern weather. The animals did not know they would become fossils. Most did not. Fossilization is rare, and fame is rarer. The famous species are representatives of a far larger vanished population whose bodies left no trace. For every Tyrannosaurus skeleton found, countless tyrannosaurs disappeared completely. For every Triceratops skull in a museum, countless horned faces returned to soil without fossilizing. For every preserved nest, countless eggs broke, hatched, rotted, or were eaten without record. The fossil record is not the past itself, it is what the past managed to keep. And what it kept is enough to change how we imagine America. Beneath modern states lies a continent that has been sea, island, coastal plain, forest, flood basin, and ash field. Beneath roads lie sediments that once held river channels. Beneath farms lie marine rocks from the inland sea. Beneath badlands lie the last bones of animals that never saw a human world. The present is built over older maps. Those older maps are reconstructed from many kinds of evidence. Sedimentary structures show flow direction and water depth. Fossils show age and environment. Isotopies suggest climate and chemistry. Ash beds provide dates. Magnetic signals can help correlate rocks. Structural geology shows basin formation and uplift. Paleontology works best when it is not isolated from geology, because animals live on planets, not in lists. The Cretaceous planet was a greenhouse world compared with today. High sea levels flooded continental interiors. Warm temperatures allowed forests at high latitudes. Carbon dioxide levels were generally elevated, though they varied. Ocean chemistry, circulation, and climate patterns differed from modern ones. These conditions shaped where animals could live and how productive ecosystems could be. The last kingdom was not only a set of species, it was a climate state. Greenhouse does not mean uniform paradise. Heat stress, storms, anoxia in marine waters, drought in some regions, and changing coastlines all created pressures. The Western Interior Seaway itself had intervals where bottom waters were low in oxygen, affecting preservation and marine life. Warmth can increase productivity, but it can also destabilize systems depending on circulation and chemistry. The Cretaceous was rich, but not simple. Inland, the vegetation was lush in many coastal plains, but plant communities varied with drainage and disturbance. Some riverbanks supported dense growth. Levees may have held different plants than swampy backwaters. Uplands, less often preserved, may have had still other communities. Dinosaurs moving across these habitats would experience a mosaic, not a continuous wall of green. Food availability changed over short distances. A Triceratops feeding on a better drained patch may have been only a short walk from a waterlogged basin where turtles and crocodilians lived. A hadrosaur herd might cross from open vegetation into denser cover near a channel. A tyrannosaur could patrol edges where habitats met, because edges concentrate movement. Many predators, living and extinct, benefit from transition zones. Ecotones are places where opportunity passes by. Edges also preserve fossils well. River margins, lake edges, floodplain ponds, and coastal transitions receive sediment. They catch remains. They bury leaves. They collect bones transported from nearby. The places most useful to living animals are often useful to paleontologists for different reasons. Water brings life, death, transport, and preservation together. This is why so many fossil stories begin with mud. Mud takes impressions. Mud slows decay when buried. Mud holds pollen and leaves. Mud fills skull openings and protects delicate surfaces. Mud can suffocate, preserve, erase, or reveal. The last kingdom was built partly on mud, and mud is one of the reasons it can still be known. At the same time, upland dinosaurs are underrepresented because uplands erode rather than accumulate sediment. Animals living away from rivers may be nearly invisible. This bias matters for diversity estimates. The animals we know best may be those that lived near depositional environments, not necessarily those that were most common everywhere. Some missing species may belong to habitats the rock record rarely preserves. Preservation bias is one reason paleontologists avoid simple claims when possible. A fossil-rich coastal plain may make lowland animals look dominant. A lack of mountain fossils does not mean mountains lack dinosaurs. A marine deposit with dinosaur fragments may overrepresent animals whose remains washed into rivers. Understanding the last kingdom requires reading both presence and bias. Even with those limits, the North American late Cretaceous remains unusually informative. It gives repeated faunas across formations and regions. It provides enough specimens of some animals to study variation and growth. It preserves plants, invertebrates, microvertebrates, and sedimentary environments. It allows comparisons between older Campanian systems and younger Maastrichtian systems. This depth is why the final American dinosaur kingdom remains central to extinction studies. Few prehistoric worlds are known with such texture. We can name the predators and prey, but also the turtles in the water, the plants on the bank, the ash in the sediment, the pollen in the clay, the bite marks on bone, the eggshell in the nest, and the boundary above them. It is still incomplete, but it is enough to feel inhabited. The emotional pull of the final kingdom comes partly from timing. It is close to us by dinosaur standards. 66 million years is immense, but within the Mesozoic, it is the near edge. The animals of Hell Creek are the last non-avian dinosaurs before the modern world begins its long approach. They are not primitive beginnings. They are late, specialized, and fully evolved. They represent dinosaur success at its final moment. That success is why their extinction lands so heavily. If they had been dwindling shadows, the ending would feel different. Instead, we find powerful herbivores, apex predators, complex plant communities, and diverse supporting fauna. The asteroid did not erase a failed experiment. It ended a dynasty still capable of filling landscapes with large bodies. But dynasty is only a metaphor. The real animals did not inherit rule through bloodlines in any conscious sense. They evolved, reproduced, competed, dispersed, and died. Their kingdom is our way of naming ecological dominance across time. It helps us hold the scale, but it should not turn animals into symbols only. A Triceratops was not a knight. A Tyrannosaurus was not a king. They were organisms in a specific world. The more specific they become, the more real they feel. Not thunder lizards in an abstract age, but animals with replacement teeth, growth stages, injuries, gut contents, nesting strategies, sensory systems, and habitats. The kingdom becomes less like legend and more like natural history. That is where its power is. The last kingdom also asks us to think about continuity across extinction. The plants recovered, rivers kept flowing, sediments kept accumulating, birds survived, mammals expanded, crocodilians and turtles continued. The continent did not end, it changed tenants. The rooms remained in altered form, and new animals entered spaces made vacant. Geological time is full of such replacements, but few are as visible as this one. The Paleogene world above the boundary was not the modern world. It was still warm in many intervals, still changing, still populated by unfamiliar mammals, birds, reptiles, and plants. The absence of non-avian dinosaurs did not instantly produce grasslands, horses, elephants, or humans. Those came much later. The immediate aftermath was recovery, experimentation, and ecological rebuilding. The shadow of the Cretaceous lingered in survivors and in empty rolls. From that perspective, Cretaceous America is not separate from us. Its extinction shaped the later evolution of mammals, birds, plants, and ecosystems that eventually led to the world humans inhabit. The continent under our feet was rearranged biologically by the disappearance of its dominant land animals. Without that extinction, the history of mammals would have been very different. The last dinosaur kingdom is part of our own prehistory by absence. But it should not be valued only because it made room for us. It had its own completeness. It deserves attention before it becomes a cause. The rivers, forests, seaways, and animals of Cretaceous America were not waiting to be replaced by mammals. They were the world, for as long as they lasted. This is why the final return belongs with a physical object rather than a lesson. A tooth, a footprint, a skull, a leaf, a boundary clay. Objects keep the story honest. They prevent the final thought from floating away into slogans. The last kingdom was made of bodies, and bodies leave pieces. The pieces are where we meet it. Hold the tooth again in imagination. Its serrations are small, but each one had a task. Its enamel formed inside a jaw that grew from nutrients taken from prey, which fed on plants, which grew from sunlight, water, soil, and Cretaceous air. The tooth is a point where the whole ecosystem narrows into one edge. Predator, prey, plant, river, climate, and time all meet there. A footprint works differently. It is not body tissue, it is a surface response to weight. The animal pressed down and left. No part of the animal remained, yet the track may outlast bone. Footprints are fossils of contact. They preserve the relationship between body and ground. A trackway is not a skeleton of an animal. It is a skeleton of movement. A leaf impression is another kind of contact. Plant against sediment. Veins pressed into mud. A season ending, a flood settling, a pond receiving what fell from branches above it. The dinosaurs around that plant may never be preserved, but the leaf tells us what fed the air, shaded the ground, and supported the food web. The kingdom depended on leaves as much as teeth. The boundary clay is contact at planetary scale. Dust from an impact, chemical signatures from catastrophe, particles spread around the world and settled into sediments. A thin layer carries a global event. Below it, the last Cretaceous ecosystems. Above it, recovery. The clay is not dramatic to look at, but it is one of the most dramatic objects Earth has made. Together, tooth, footprint, leaf, and boundary hold the story in 4 scales. Individual feeding, individual movement, ecosystem foundation. Planetary Cretaceous America can be approached through any of them, and each leads back to the others. That is what makes the last dinosaur kingdom so difficult to reduce and so rewarding to follow. The story could close with the asteroid, but the rocks do not. It could close with Tyrannosaurus, but birds continue. It could close with loss, but fossils remain. The better ending is quieter. A hillside after rain. A bone edge in clay. A bird above it. The modern world carrying the ancient one under its surface. There is no need to make the past speak louder than it does. It is already loud enough in stone. A tooth in a slope can open a seaway. A skull can bring back a floodplain. A nest can return a season. A thin layer of clay can mark the fall of a world. The last dinosaur kingdom is not a myth beneath America. It is geology, biology, catastrophe, and survival, written in pieces and still being read. To make the final kingdom feel less like a chart and more like a place, follow one ordinary day on a western floodplain near the end of the Cretaceous. Before sunrise, the air is warm and wet. Mist gathers above low ground. Water stands in shallow depressions left by the last flood. Insects move before the larger animals do. Small mammals return to cover. Birds shift on branches. Somewhere near the river, a crocodilian waits with only part of its head above the surface. light reaches the tops of the trees first. The canopy is not a modern oak forest, and not a Jurassic forest either. Flowering plants are part of the understory and river margin. Conifers and other older lineages remain. Ferns fill damp places. Horsetails grow near water. Fallen leaves collect in still pools. Roots hold some banks and fail on others. The plants are doing the work that every large animal depends on, turning sunlight into tissue before any tooth or beak touches them. A group of Edmontosaurus begins feeding along a slightly raised surface near the channel. Their heads lower, jaws working with a motion unlike simple reptile biting. Plant material moves through beaks and into dental batteries where tooth surfaces grind and shear. The animals are large enough that their movement bends small trunks and opens paths through vegetation. Younger individuals keep closer to the group. They are safer there, but not safe in any absolute sense. Nearby, a small theropod watches the disturbance for a different reason. Large herbivores flush insects, lizards, and small animals from cover. The hunter does not need to challenge a hadrosaur. It uses the herd as weather, as movement, as an ecological force that exposes smaller prey. This is how ecosystems layer opportunity. One animal's feeding becomes another animal's hunting ground. Farther away, a Triceratops feeds in heavier cover. Its beak clips vegetation, and the jaw muscles behind the skull bring force into the tooth rows. The animal's horns and frill are obvious, but most of the day they do nothing dramatic. They are carried like any other part of the body, heavy and familiar. The head turns toward sounds. The nostrils test the air. The animal shifts its stance, plants one forefoot in mud, and leaves a broad impression that will vanish unless sediment protects it. A Tyrannosaurus moves along the edge of the river corridor. It is not charging. Large predators conserve energy. Its pace is deliberate, its head active, its senses reading the landscape in ways we can only infer. It may be following scent. It may be moving between known places where carcasses sometimes collect. It may be aware of the hadrosaurs long before they are aware of it. In a living ecosystem, danger often begins as information. The hadrosaurs do not scatter at every distant sound. Constant panic wastes energy. Prey animals assess risk. They respond differently to a predator far away, a predator approaching, a predator hidden, or a predator already attacking. The fossil record rarely preserves this behavioral judgment, but it is essential. Survival is not only speed, or it is knowing when to keep feeding and when to move. In modern ecosystems, large carnivores fail often when hunting healthy adult prey. There is no reason to imagine Cretaceous predators were exempt from the same economics. Injury is costly. Energy matters. Prey fight back, flee, gather, hide, or choose difficult terrain. A tyrannosaur could be dominant and still cautious. An apex predator is not an animal that wins every encounter. It is an animal with no regular predator above it. By midday, heat changes behavior. Large animals seek shade, water, or slower movement. Smaller animals retreat into cover. Insects continue their work. The river carries sediment from upstream, fine particles in suspension, and coarser grains along the bed. A cut bank collapses. Roots tear free. An old bone, perhaps already fossilizing from an earlier deposit, may be exposed and destroyed before anyone can ever know it existed. The Cretaceous fossil record includes reworked material, bones eroded from older deposits and buried again in younger ones. This can confuse interpretation if context is poor. A bone may be older than the sediment that finally holds it. A tooth may travel. A shell may be moved from one environment into another. The rocks preserve history, but sometimes the history has been edited by water before burial. Afternoon storms build over the lowland. Rain arrives first as scattered drops, then as a heavy sheet. Tracks soften. Small channels fill. Plant debris moves downslope. A nest in a vulnerable place may flood. A carcass near the bank may be lifted rolled, and carried into deeper water. Sediment covers some evidence and erases other evidence. The same storm that kills or destroys may also create the conditions for preservation. This is the paradox of the fossil record. Catastrophe at small scale is often preservation at large scale. A flood that destroys a nest can bury eggshell. A drought that kills animals at a shrinking pond can form a bone bed. A volcanic ashfall that stresses a landscape can provide a datable layer for future science. The rock record is filled with harm converted into information. Evening returns with cooler air. The river is higher now. The hadrosaurs have moved. The Triceratops stands on firmer ground. The Tyrannosaur may have found nothing, or it may have found the beginning of a carcass exposed by the storm. Birds settle. Insects change their calls. The floodplain absorbs water, weight, and scent. Nothing in the scene announces that it belongs near the end of an era. It is simply another day inside the Cretaceous. That ordinary quality is important. Deep time is often described through extremes because extremes survive in attention. Largest predator, strongest bite, biggest horns, final extinction. But the animals themselves lived through sequences of ordinary days, feeding, resting, moving, growing, avoiding risk, reproducing. The last kingdom was not made of highlights. It was made of repetitions that continued until one event made repetition impossible. A similar day in Appalachia would be harder to reconstruct, not because it lacked life, but because the evidence is thinner. Eastern rivers carried bones toward coastal and marine settings. Forests covered places where exposures are rare. Later erosion and vegetation hid or removed many records. The animals there may have experienced humid lowlands, coastal systems, and upland habitats we only partly glimpse. Their obscurity belongs to preservation, not importance. Somewhere on that eastern landmass, a Dryptosaurus-like predator may have moved through forest openings with stronger arms than its western tyrannosaurid relatives. Hadrosauroids fed in lowlands. Armored dinosaurs carried plates through vegetation. Small theropods hunted under cover. The scene is less detailed than Hell Creek, but it should not be empty in imagination. A fragmentary fossil record is still a record of living animals. A similar day in Alaska would be stranger still. The sun angle would change the rhythm of the year. In the light season, plants would grow quickly, taking advantage of long days. In the dark season, animals would face months of low light or darkness. Some may have migrated. Others stayed. Juveniles in polar deposits suggest reproduction in high-latitude regions, complicating the idea of simple seasonal escape. The North was not a side note. It was a test of dinosaur adaptability. High-latitude dinosaurs show that the group tolerated a wider range of environments than older views allowed. Warm Cretaceous climates made polar life possible, but seasonal darkness remained. Animals there still needed feeding strategies, growth strategies, insulation, and reproductive timing suited to the environment. The fossil bones from Alaska are therefore not just northern curiosities, they are evidence of ecological breadth. A southern day with Alamosaurus changes scale again. In latest Cretaceous Texas, the presence of titanosaurs means that one of the oldest dinosaur body plans, the giant long-necked herbivore, still had a place in North America. The animal's feeding would have affected vegetation at heights beyond the reach of hadrosaurs and ceratopsians. Its carcass, when death came, would have fed an entire community. Its bones, if buried, would preserve a different final kingdom from the northern plains. Under the same broad Cretaceous sky, then, America held horned herds in the north, titanosaurs in the south, fragmentary eastern faunas, polar dinosaurs in Alaska, marine reptiles in the interior sea or its remnants, birds in trees, and pterosaurs above open ground. No single camera could capture it all. The kingdom was too wide, too long, and too varied. It has to be assembled from places that never fit into one living view. This assembly is the work of evidence and reconstruction together. Science provides the constraints. Careful reconstruction provides continuity without pretending the gaps are gone. The result should feel like walking along a series of outcrops, each one adding something. A tooth here, a leaf there, a dated ash bed, a nest horizon, a marine shell, a boundary clay. The path is not straight, but it leads toward understanding. At the end of that path, the tooth in the gray stone remains small. It does not become larger because the story is large. It becomes more precise. It belonged to a mouth, to an animal, to a food web, to a continent, to a period, to a boundary. The last dinosaur kingdom is contained there only because everything living is connected to more than itself. Collections matter, because not every discovery happens in the field. Many fossils gathered years ago still hold information that earlier researchers could not extract. A bone prepared with old tools can be scanned with new ones. A tooth catalogued as isolated material can become important when compared with a new sample. A fragment once set aside may show growth, disease, or a range extension. The last dinosaur kingdom continues to change because the archive is still alive scientifically. In that sense, the kingdom survives partly as work. Not living work, but human attention applied to ancient remains. Measurements, photographs, thin sections, maps, databases, and careful descriptions turn stone back into knowledge. Each specimen is limited, but together they create a record dense enough to reconstruct rivers, shorelines, diets, growth, injury, and extinction. The animals are gone, but the evidence is not finished speaking. The most powerful fossils are often the ones that do not seem powerful at first. A flake of eggshell, a fish scale, a worn tooth, a root trace crossing a layer of mudstone. These pieces do not carry the spectacle of a mounted skeleton, yet they hold the world in place. They remind us that Cretaceous America was not only giant bodies in dramatic poses, but countless small contacts between life and sediment. The strongest way to hold the scale is to compare lives across time without collapsing them together. Acrocanthosaurus lived closer to the beginning of the Cretaceous than to its end. The ornate ceratopsians of the Campanian lived millions of years before Triceratops. Tyrannosaurus arrived so late that much of the Cretaceous had already passed into rock before its lineage reached that final form. The American dinosaur kingdom was not one caste of animals, but a succession of castes, each replacing or modifying the one before it. A formation boundary is often more meaningful than a famous name. It marks a change in rock, environment, age, or all three. The Cedar Mountain is not the Hell Creek. The Kaiparowits is not the dinosaur park. The Niobrara is not a dinosaur floodplain, but a marine record of the inland sea. When these names are kept distinct, the continent gains depth. Each formation becomes a room with its own light, animals, sediments, and problems. A visitor to the modern outcrops might stand in one place and see several colors of sediment stacked across a slope. Gray mudstone, tan sandstone, darker carbon-rich layers, pale bentonite seams. To a casual eye, it is a weathered hillside. To a geologist, it is movement through environments: channel, floodplain, soil, ash, swamp, overbank mud, perhaps the approach or retreat of a shoreline. The dinosaurs lived inside those changes, not above them. The last kingdom also had a smell, though no fossil can keep it. Wet clay, crushed leaves, standing water, animal dung, resin, decay, smoke after distant fire, and the mineral scent of rain on warm sediment. Smell is part of animal decision-making. It tells a predator where flesh may be. It tells a herbivore where water, other animals, or danger may be. It tells insects where to gather and mammals where to hide. The Cretaceous was chemical before it was visual. Sound would have traveled differently through each habitat. Open banks carried calls farther. Dense vegetation broke them apart. Water reflected and swallowed them. A large animal moving through brush was not silent. Branches cracked, mud pulled at feet, lungs moved air, and low sounds may have passed between members of a group. The exact voices are gone, but the need for sound remains clear wherever animals had to find, warn, attract, or avoid one another. These missing senses are why the fossils feel both close and distant. Bone brings back form, tracks bring back motion, leaves bring back habitat. But the full experience of the kingdom is gone. What remains is enough to build the outline, and sometimes more than the outline, but never the complete presence of a living day. The gap is not a failure. It is the distance between evidence and life. The more carefully we look, the less the Cretaceous feels like a single age of monsters, and the more it becomes a set of living systems. Dinosaurs were successful because they were varied. They ate different foods, grew at different rates, defended themselves in different ways, reproduced in different strategies, and inhabited different climates. Their kingdom was not fragile because it lacked diversity. It was vulnerable because even diverse systems can be broken by events large enough to interrupt the base of life. In the end, the last dinosaur kingdom in America leaves us with no single final sound. Not a roar, not a crash, not a clean silence. It leaves a boundary in the rocks, a missing future for many lineages, and living birds above us. It leaves bones weathering from badlands and teeth slipping from hillsides after rain. It leaves museum halls, field notebooks, quarry maps, and small paper labels under fossils that once belonged to bodies moving through heat, mud, and forest shadow. The tooth in the stone is only a tooth. It cannot carry the whole continent, but it can open it. From that small serrated edge, the rivers return. The seaway fills the interior. The western plains darken with herds. The eastern forests stir with animals we barely know. The polar woods enter their long season of low light. The southern giant lowers its neck to feed. A horned face turns beside a river. A tyrannosaur breathes over wet ground. Then the rain stops on the modern hillside. The mud settles. The tooth remains where erosion placed it, held between the world that made it and the one that found it. Around it, the grass moves in ordinary wind. Above it, birds cross the sky. Beneath it, the last dinosaur kingdom is still there, not alive anymore, but not entirely gone, waiting in bone, ash, leaf, track, shell, and stone.